ரெண்டுத்த அன்மியூட், ஆமா ரெண்டுத்த அன்மியூட் பண்ணி வச்சிருக்கேன் சார். ஒன்னு வந்து அந்த இதுவும் வீடியோவும் ஆடியோவும் போதுமா? அதை அன்மியூட் பண்ணிட்டேன். நேஷனல் ஒர்க் ஷாப் மாடலிங் ஃபார் ஹை டைமென்ஷன் ஸ்டாட்டிஸ்டிக்கல் டேட்டா மாத்திட்டாரு. ஐயா இப்ப என்ன பண்ணலாம் சொல்லலாமா அவர்கிட்ட?
சார் என்ன போடணும் சொல்லுங்க.
அவர்கிட்டே பேசலாமா?
என்கிட்ட பேச நான் பேசுறேன் உங்ககிட்ட.
ஓ
சார்
சார் என்ன பண்ணணும் சொல்லுங்க.
ரஹீம் சார்.
ஹலோ சொல்லுங்க சொல்லுங்க கேக்குது சொல்லுங்க.
ஸ்டாட்டிஸ்டிக்கல் மாடலிங் ஃபார் ஹை டைமென்ஷனல் டேட்டா சார்.
ஓ ஸ்டாட்டிஸ்டிக்கல்
மாடலிங் ஃபார் ஹை டைமென்ஷனல் டேட்டா.
ஓகே ஓகே ரைட். அப்படி ஒரே செகண்ட்.
சரிங்க சார்.
ஓகே நோ ப்ராப்ளம்.
சார் எனக்கு வீடியோ வரல.
நீங்க வந்து நீங்க கீழ வந்து மோர்ல போய் இது எடுங்க மேடம். வீடியோ வந்து ரிசீவ் பண்றதுக்கு ஓகே பண்ணிக்கோங்க. ஏன்னா வீடியோ நீங்க ஆஃப் பண்ணனா பண்ணிக்கலாம்.
ஆஃப்ல இருக்கட்டுமா சார் எனக்கு வீடியோ?
இல்ல நீங்க வீடியோ வரலனா நீங்க இல்ல மேடம் நீங்க வீடியோ ஆன் பண்ணுங்க மேடம் கீழ.
ஆன் பண்ணிட்டேன் சார்.
ஹலோ குட் மார்னிங் டாக்டர் பிஆர் ஜெயஸ்ரீ.
குட் மார்னிங் சார்.
குட் மார்னிங். ஓகே அந்த இதுல டைட்டில் தப்பு இருக்க மாதிரி
இருக்கு. மாத்த சொல்லிட்டேன் சார்.
ஸ்டாட்டிஸ்டிக்ஸ் மாடலிங் ஃபார் ஹை டைமென்ஷனல் டேட்டா.
ஸ்டாட்டிஸ்டிக்கல் மாடலிங் ஃபார் ஹை டைமென்ஷனல் டேட்டா மாத்திட்டேன்.
ஆமா ஆமா ஆமா.
சொல்லிட்டேன் சார்.
மாத்தியாச்சு பாருங்க. சேஞ்ச்டு சார்.
Thank you sir.
Thank you bro sir.
Good morning Indian sir.
இப்ப கேக்குதா?
நீங்க பேசுறது கேக்குது.
இப்போ நான் வந்து அத மியூட் பண்ணிட்டேன்.
மேடம் பேசுறது கேக்குது. இப்போ மேடம் பேசுறது கேக்குது. நீங்க பேசுறது கேக்குது. நான் பேசுறது கேக்குதா?
எஸ் சார்.
சார் கேக்குது.
ஓகே.
சார் நான் பேசுறது கேக்குதா?
கேக்குது. இல்ல இப்போ நீங்க மியூட் பண்ணிருக்கீங்க. எடுத்து விடுங்க. இப்போ வரும்.
Very good morning to one and all present, virtually present in this workshop. At the outset, I must congratulate the Department of Statistics, especially the HOD, Dr. Prakash sir, and Organizing Secretary, Dr. Viswanathan sir, and all faculty members of statistics for conducting this nice workshop. Now, IQAC has already announced that it is ready to support any individuals or the departments who are ready to conduct webinars by the technical means. Some of the departments, they have completed the webinars also, but statistics is the first department which comes with an idea of conducting such extensive workshop. In fact, really they approached me for 3 days program, entire 3 days program they asked for. But due to the time limitations and demand from other departments, we only asked them to restrict the program for 2 days. And of course, the statistics department is also kind enough to adjust themselves to conduct the program within 2 days. And I thank them. And it is a very good venture. The first time we are also having the first experience, you know, you are going to conduct a very extensive program for the 2 whole days. Really appreciate the department once again. And with these few informal words, I hand over the platform to the Department of Statistics. I think probably the Madam Jayashree, Madam will be the convener of this event. Madam, please unmute yourself and you can take over the session, Madam, please.
Good morning, all. First of all, I would like to thank Rahim sir and the IQAC team for providing us this platform and for the compliment given to us. Big data is at the foundation of all megatrends that are happening today globally, and data is ruling the world. So it's a great pleasure in welcoming you all to this 2 days national workshop on statistical modeling of high dimensional data that's going to be happen for today and tomorrow, organized by the Department of Statistics, Presidency College, Chennai. So first of all, I would like to thank our dynamic principal in charge, Professor Devanathan sir, for giving us this platform to conduct this workshop. And I also thank the IQAC team for their technical support. Indeed, I need to thank all the participants who have supported us and the overwhelming response we have during this pandemic situation. So with this few words, I invite our HOD, Department of Statistics, and he is the convener of the webinar to address the participants and to deliver the welcome address. Thank you.
Sir, please unmute yourself and speak, sir. Please unmute yourself, sir.
Good morning to one and all. Extend a warm welcome to all. It's my great pleasure to welcome our Principal Dr. Devanathan to this national webinar on statistics modeling for high dimensional data. And also I thank him for his enormous support to conduct this program. And the next, I extend a warm welcome to the resource persons of this webinar, Dr. M.R. Srinivasan, retired professor of University of Madras, then Dr. P. Venkatesan, Director ICMR retired, And then Dr. Sampath, retired professor from University of Madras, and Martin Luther Williams from Laila College, and Dr. Punraja from ICMR, and Dr. Vishnuvardhan from Pondicherry University. And it's my great pleasure to welcome our department staff who supported me to conduct this program. At this conjuncture, I wholeheartedly welcome them to this webinar. And also, I extend a warm welcome to HOD and staff member of other departments from Presidency College, from various departments to this webinar. And wholeheartedly, I am very happy. I would like to give a warm welcome to the IQSC Director, Dr. Rahim, and his Mrs. Madam Dr. Lalita, to this webinar, and both they supported us to conduct this program right from the beginning. And I'm very happy. It's my immense pleasure to welcome all the participants to this webinar. I hope that you will all enjoy with this program, and definitely you will be enlightened your knowledge by your resource persons. Thank you. Thank you.
Thank you, sir. Now I invite our dynamic principal in charge, Professor Venkatesan, sir, to deliver the inaugural address.
Good morning, one and all here present, though virtually from the safety of their homes. I am really pleased that the Department of Statistics is organizing a lovely and a beneficial two-day webinar. When they approached me for this webinar, I readily accepted because we all know that the world moves on two things, yen and எழுத்து. Without yen and without எழுத்து, nothing can move. That is why it is expressed by Tiruvallur, எண்ணென்ப ஏனை எழுத்தென்ப. So I know that this webinar is going to be of immense help to those who have enthusiastically participated here. For this, I wholeheartedly congratulate the Department of Statistics, its HOD, the dynamic members of the department, and all those students who are out there to gain knowledge through resource persons of immense experience. So it is not just passing of knowledge alone, but passing of experience. That we have resource persons of immense experience will definitely throw good light for our students who are out to be better individuals and very good statisticians in future. So I will be happy to congratulate the department, the HOD Dr. Prakash, all the organizer Dr. Vishwanathan, comparer Madam Jayashri, and all the other staff members. I really congratulate them, and a special word of praise is for the IQAC team, which is led by Dr. Abdul Rahim. So I wish all success for this webinar. I hope that our students would be benefited by the words of enlightening words of the experienced speakers. I wish all success. Thank you for giving me this opportunity. Thank you all.
Thank you, sir, for your supporting words. And now we will move on to our first session, which is a legendary professor. He is a retired professor from University of Madras, and he is a data analyst, Dr. B. Sampath, sir. And I will hand over this session to Professor Vishnuvardhan, sir, of our department, and he is the organizing secretary for the webinar. So over to Viswanathan, sir.
Thank you, madam. Good morning to one and all. On behalf of the Department of Statistics, Presidency College, the faculties, the research scholars, students of Fraternity of Statistics, I welcome Professor Sampath for this webinar on statistical modeling of high-dimensional data. Professor Sampath has a versatile experience across different platforms, especially teaching, research, industry, and whatnot. He has a very good experience over all these domains, possibly around 40 years. Professor has got his PhD from the University of Madras in 1991. He was serving with Lyra College in the initial tenure of his life, and then he switched over to Birla Institute Institute of Science and Technology, Dubai, UAE. Then he moved to University of Madras, and to his credit, he has 10 completed research scholars for PhD. His area of interest and research is wide open. To mention a few, he has great many interest in the theory of finite populations, credibility theory, testing and estimation of parameters in imprecise model and data mining. He has got published nearly 60 research papers in high-rated national and international publications, journals. Also, he authored a book under sampling theory, under the title Sampling Theory and Methods, published by CRC Press and Narosa Publishers. And it was a very good book for PG statistics, especially in the sampling area. And professor has a unique knowledge or talent, so to say, to visualize and transfer complex statistical models into simple terms for the viewers. So these kind of things will have very, this is a very rare skill, so to say. And as many philosophers like Jiddu Krishnamurti, who used to say word is not a thing, but I think today's words of Professor Sampath will bring you very close to the thing. And in particular, he is going to deliver the topic on principal components and its application using Python. It's actually a two-in-one. It's a treat to watch is theoretical excellence combined with his computing skills in Python. So I welcome Professor Sampath to take over the stage and deliver the result. And of course, within the time limits, because we are running out of time. Now, for every other participants also, we have to share the time. So I now hand over to the professor's task.
Yeah.
Professor Sampath.
Yeah. Good morning to everyone. First of all, I would like to thank Dr. Prakash for considering me as a resource person for this webinar. Next, I would like to thank Dr. Viswanathan, who happens to be my one of my earlier period students. He was telling so many things. I do not know whether I really deserve or not. But in my opinion, you are also one of the teachers who show interest in plenty of branches of statistics, computer science, etc., etc. So I'm really proud to be a teacher for Dr. Viswanathan. So with these words, it is better to start the technical points. So actually, when Dr. Prakash approached me, he said, you give a talk on sampling theory. But I feel not many will be interested in listening to the theory, which is slightly getting outdated. So in my opinion, perhaps you may have a difference of opinion. So then immediately I said, I'll give you a talk on R. No, he said, no, everybody knows R, so you don't stick to R. So he, motivated by his suggestions and etc., I have decided to make use of Python for this small 1 hour duration lecture. It won't be very extensive, but given the maturity level you have, I hope we'll be able to take on from where I am going to leave you. So in order to get some insight into the working of Python, I have decided to take some topic in statistics. Probably I could have considered introductory statistics or descriptive statistics or testing, etc. But more beyond that, I have a feeling that something related to multivariate analysis will be better for this kind of audience, because those elementary things anyone can teach. But this PCA, I have a different type of understanding. Based on my interaction with people working in machine learning, etc., I have a feeling that still there are some points which need to be explained properly. So with that idea only, I have decided to take up the principal components. So I have planned the lecture like this. About 30 or 35 minutes I will use for PCA. Then I will tell you how to make use of Python for giving the demo, etc. So this is my primary idea behind this lecture. So I hope, is my screen visible, Dr. Viswanathan? Can you see my screen, Viswanathan?
No, sir. Sir, please share your screen, sir.
Yeah, I'm sorry.
You have to share the screen.
Yeah, now can you see?
Yes, sir. Yes, sir.
Okay, fine. Now, so that is idea behind this lecture. So, so just a minute. Sir, you can just give me rights for recording because people are entering. I am forced to see that also.
We will admit the participants, yeah. No problem. You can just please carry out the presentation, sir. No problem, sir.
Now can you see the screen, sir? With
yes, sir. Yes, sir. Yes, sir.
Oh, fine. Thank you. So the topic, as I said, happens to be the principal component analysis with some little bit of applications in the Python. So in fact, I wanted to use another device where I can write Surface, but there is some problem in sharing the files. So probably I may not be able to write anything on the whiteboard. If you have any confusion, we can clarify a little later. So the main objective of about this lecture, I would like to spend a few minutes. So the main purpose is to create a kind of awareness.
Sir, excuse me, you can use the annotation also, sir. If you want, you can use annotation.
It is necessary to write some this thing, sir.
Yes, sir. We have provided annotation option also. Whiteboard also is there, sir. So you can use anything.
Whiteboard, here I have a problem with my.
Okay, sir. Okay, sir. Okay.
Yeah, this device will not accept that Silex pen. Okay.
Okay, thank you, sir.
Yeah, welcome, sir. So, it is the exercise is mainly to create an awareness among researchers regarding the usefulness of open source softwares like R, Python. Now, sometime back in one of our discussion group, somebody was advocating the use of even Julia also. So many things are there. So plenty of softwares are available which are free. Main advantage of these open source softwares is you get state-of-the-art technology. So, for example, if you are going to use something like SPSS or SAS, whatever it may be, so they will take some time to bring it into the market. So, whenever somebody promotes or whenever somebody develops an algorithm, so immediately he comes out with a package which the researchers can immediately make use of. So, that is the biggest advantage of tools like R and Python. So, and apart from this, I would like to give some rough idea about so various packages, how the packages are utilized in data science or statistics or machine learning, etc., etc. So it goes like that. So I have kept in my mind students for majoring in statistics, data science, and computer science, specifically UG and PG students, because at the time of teaching PCA, the semester will be nearing the end. So the teachers may not have enough time to explain the niceties of a PCA, what is happening inside, all the things will be terribly missed based on my experience. Even when I was also teaching, I had the same problem. So only towards the end of teaching multi-analysis, we'll come to a PCA, just like it will rush through. So some points which I have, which attracted me, I'm going to explain. So the level of this lecture is going to be only medium. And what I assume is elementary statistics, like what is the variance, what is covariance, what is the correlation, what is the dispersion matrix, etc. And a little bit of the knowledge in matrices like decompositions will help you to have clear idea. And scripts nowadays, they are in a readable form. So whenever you just go through the syntax, you will be able to understand what it expects, okay, what it is going to perform. So now to start with, I'm going to introduce some 3 or 4 terminologies. So for the first one is data matrix. So basically, whenever we have data sets which we come across in machine learning or whatever field we are working, we make use of mainly data matrices. So basically, a data matrix is a kind of a table where you, in the columns will have variables. So here I have shown you one data matrix which I have taken from R. So this is a data matrix which explains details related to the findings of urine analysis. So here we have something like 6 variables, and then we have one classification variable like this gravity, pH, osmo, etc., etc. They are all variables, and what we have is that in the first column we have R. So this is the kind of data matrices we come across whenever we do data analysis. So then once we have the data matrix, next comes basically when we want to perform principal component analysis, we often make use of the term covariance matrix. So if you have a data matrix consisting of say about 5 or 6 columns, so in my data I had about 6 columns. So the covariance matrix will have 6 rows and 6 columns, 6 rows and 6 columns. So the diagonal elements will be your variances. See, for example, this 0, why it comes to the values. So I have rounded up for 3 decimals, so that is why it is showing 0. Otherwise, it will be a constant. So it won't happen like that. So if you have a look at this data here in this column, you can notice that the amount of variation is very little. Since I wanted to put it in the slide, I have truncated. As a result of that, you can see 0, so it should not be considered as 0. So some value which is different from 0 is there. So we have in the diagonal elements, you have the variances, and in the non-diagonal elements, you have covariances. So this is how we make use of, we come across the variance covariance matrix. So the notion of variance covariance matrix is very much needed if you want to know the technical background or the full utility of a PCA. So that is why I have spent some time. So on the non-diagonal elements are covariances. So non-diagonal elements are covariances. So for example, this 546.385 is a covariance between the urea and this attribute COND. Understood? So complete description about this urine data set we can get from R. For lack of time, I'm not spending much time on explaining what are the variables, etc., etc. It is a very popular data set which is frequently used by people working in data science or machine learning, statistics, etc., etc. Okay. So non-diagonal elements are covariances, and the diagonal elements are the variances. This is our understanding. And the next one, the most important thing which we have to understand here is the generalized variance. So the principal see, whenever somebody suspects the utility of the principal components, we defend its usage with the help of the generalized variance. So what we say now, so the generalized variance we define as the determinant of the covariance matrix. So determinant of the covariance matrix is known as the generalized variance. Then comes the correlation matrix. So here all the diagonal elements happen to be 1. That means naturally the covariance between x and x will be 1. So on the non-diagonal elements were correlations. So this is the basic difference between covariance and the correlation. So these things are much needed for our discussion. Okay, now coming back to this, often I have seen people working in machine learning, they tell we want to go for a dimension reduction technique. We want to go for a dimension reduction. So immediately they start making use of PCA or singular value decomposition or whatever it may be. They make it. So dimension, sir, or the host, sir, please could you, yeah, sir, could you please hide the waiting room entries? Yeah.
Okay, okay, sir.
Because that is causing some distraction. Not only I'm not able to see. So what we mean by the dimension of the data set is, see, suppose we have a data set consisting of like what I have told earlier. Suppose I have a data set like this. Here, the dimension of the data set happens to be 7. So of course, one classification variable is there. So if you leave it out, so you have a data set consisting of 6 dimensions. Now, normally, when nowadays people who work in machine learning, they come across a data set consisting of sometimes 100 or even sometimes thousands also they get. See, for example, if you take a stock market data set, so in the columns you will have various companies. Various companies will find place in the columns, and in the rows you will have, for example, days of transaction. For example, yesterday's closing price of a particular stock can be taken as one variable. So when you deal with a data set like this, we'll be having columns. Number of columns will be in hundreds. So some columns will be informative for the system. Some of them may not be that much informative. So that is what we are going to discuss when we move further. Okay. Now, so now I'm keeping track of the time. Okay. So dimension means the number of columns in the data set. So normally we statisticians call column variables. We call those columns as the variables. Column headers are called as the variables. And here in people working in machine learning or computer science, people they call as the features. Because now my recent connection with a group forces me to relate variables. So, see, suppose we use the word variables, attributes, etc. Audience will get confused. So from now onwards, I'm going to use the term feature. Feature means a variable. So what is the aim of the principal component? So principal component analysis aims for the reduction of the number of columns. So suppose we have 100 columns or 200 columns, then we will try to represent the entire data with the help of a smaller number of columns. That is what we mean by dimension reduction. So basically, dimension reduction means reducing the number of columns. But remember, suppose we have some 500 columns, reducing the number of dimensions means it is not simply throwing away some of the existing variables. It is not at all like that. So more about that we'll explain a little later. So it is not that reducing the dimension means elimination of some original features and retaining some of them. So it is not at all like that. So what we do here is we go for a new representation. That means we create a new feature space. See, originally you have a p-dimensional feature space. That means when we have 6 variables, we have a 6-dimensional feature space. And when we go for principal component analysis, there also we create a feature space containing exactly the same number of features. Suppose you have in the original space, say 10 variables. Definitely we have 10 variables in the new feature space also. Then you can ask me what is interesting here. That is what we are going to tell now. Now, one more thing which I want you to understand is when we have the original feature space, we can identify the columns with some physical quantities like specific gravity or whatever it may be. So we can give names for those attributes, whereas that is not possible in the case of new feature space. So new feature space are hypothetically created features which are going to play an important role in performing dimension reduction. So that is what I have mentioned in my last bullet. The features in the original space can be identified with the help of the variables which are being studied under the given domain. On the other hand, newly created variables or features cannot be easily associated with the existing features, but they have a correlate, they have a relation, which I will explain a little later. Okay, so this is what I have. So now for people who are technically minded, you can just remember this. So I have originally a three-dimensional data space consisting of n vectors. So in machine learning language, they call this as a record or whatever it may be, or an instance. So they call even that as an instance also. So you have a three-dimensional data set consisting of n vectors, and we denote those features, those variables, those p variables by x1, x2, etc., xp. Remember, X1 is one particular column name, X2 is another particular column name. So it goes like that. So originally we have P columns. So when we have n instances, your data matrix will be having the dimension n cross p, where n is nothing but the number of instances. Now comes the question of formally defining what are principal components. So the principal components are, sir, will the Stylex work on annotation, sir?
Yes, sir. Annotation works, sir.
Annotation works, but the Stylex pen, will it detect? That is a problem. Okay, so yeah, so now no problem. So principal components are basically normalized linear combinations of the original variables which are uncorrelated with each other. To help you understand this sentence, I have given one small example. See, here I have one data set. So this is a very famous data set which we have in the literature. So it is called the iris data set. So what happens, those who are familiar with the iris data set, you may be remembering there will be 4 features. One is the sepal length, the other one is sepal width, the third one is petal length, and the petal width. So your data set has 4 features. That means it is a 4-dimensional data space. And if you remember, there will be 150 instances. So you have 150 instances and 4 features. So the data matrix will be of the dimension 150 cross 4. Now, when I perform PCA, as I said earlier, I'm saying principal components are basically the linear combinations. So I said normalized linear combinations. What it means, that I will tell you. See, suppose I go for my first principal component. My first principal component is a linear combination of these variables. So what is my first variable? First variable happens to be the sepal length. So that is like your X1. Sepal width is your X2. Petal width is the X3. And I think there is a small printing mistake. Petal length, it should have been petal length. So those 4 variables are considered here. I'm sorry, really apologize for that small typo. So the first principal component is a linear combination of the existing 4 variables. So here you can see that petal length. So it is the effect of aging process. So I have crossed nearly 61. Yeah. Okay, anyway, so basically, the first principal component is a linear combination. The second is also a linear combination. So like that, every principal component is a linear combination. So if you have a look at that particular definition, you understand. So principal components are linear combinations. Then what? What is meant by normalized linear combination? What is meant by normalized linear combination means, so if you find the norm of those coefficients like 0.3613 minus 0.0845, 0.8567 plus 0.3582, it will have length 1. So this is what I wanted to tell you. So the principal components are basically normalized linear combinations, and they are in fact uncorrelated with each other. See, as you remember, if you have a p-dimensional feature space originally, that is defined on a coordinate system where you have p mutually orthogonal axis. The same thing is expected even in the newly created space also. So basically, we are creating a new space consisting of p dimensions, understood, but they are orthogonal to each other. So that is guaranteed by that particular aspect. So y1 is your first principal component, etc. So it goes like that. Now, what I am saying now, now these two or three important points will definitely help you. Now, if you see the variances of the principal components, you see, principal components are just like the original variables, they have some variances. And so in the same way, the PCAs also will have some variances. So the first PCA will have the largest variance. This is what we'll be using a little later. And the second PCA will have the next largest. Third PCA will have the third largest. So like that, if you order the PCAs, their variances can also be will also be get automatically ordered. That is what I have given. So that is one important aspect which will make use when we go for a determination of a number of dimensions to be retained. And another thing is, this is the most important thing. See, when people suspect the utility of the principal components, they tell, see, normally what would be my recommendation? No, when I have x1, x2, etc., xp, when I have p-dimensional space, I will go for ignoring of some columns. So that means I will try to reduce the number of variables. So instead of 64 variables, I may be interested in retaining 10 variables or 15 variables. How do we determine that? I'm going to tell a little later. So we have to convince the practitioner that by ignoring certain features in the newly created space, are we not sacrificing some information? For defending that particular aspect, what I am saying now, if you consider the variances of the original variables, if time permits, I'll show you some demo also. See, for example, if I take this particular data set, so here I have the variances. So if I add all these variances, that sum will be equal to the sum of the variances of the principal components. So sum of the variances of the principal components. So suppose we have 6 variables, the number of principal components will also be 6. But when you add the variances of the original variables and the variances of the newly created variables, when are called principal components, they will be one and the same. Then you can ask me, if I throw away something, what will happen? That is where the first point comes into mind. So as we keep on proceeding further, the principal components of largest orders will have smaller variances. So by ignoring them, you will not be losing too much information. Anyway, you cannot have 100% retaining, understood? So for anything, you have to pay some cost. So there only we lose something, but that loss will not be great significant. In fact, those variances may be due to some errors also. So many things we can attribute later on. Okay. So one way of defending is the original variables will have the same sum of the variances of the original variables will be same as the sum of the variances of the principal components, newly created variables. And another point is, if you consider generalized variance, so if you consider the determinant of your covariance matrix, see, like if you find the determinant of this covariance matrix, if you find the determinant of the covariance matrix, that will be same as the determinant of your determinant of the covariance matrix of your principal components. See, remember, the covariance matrix of your principal components will be a diagonal matrix, because so covariances between the principal components are what? They are 0. So if you simply multiply the diagonal limits of the covariance matrix of the principal component, understood? So naturally, that product will be same as the product of that product will be same as the determinant of your generalized variance matrix. Okay, so this is how we define. What I am trying to tell now, so as a defense, so we'll be able to keep the same amount of variance. So original variables variances, some will be same as this one. The next one is if you find a generalized variance of the original system, that will be same as the generalized variance of the principal components. That is one thing. And one more thing, this is one particular thing which we may not use in machine learning, but people who work in multivariate analysis and exploratory data analysis, whatever it may be, there will be, there is a small domain called factor analysis, understood? So here they make use of this particular aspect. So what is important now? If you take any particular principal component, you can see there is a, if you consider the correlation between a particular principal component and a feature, understood, that is proportional to its coefficient in the linear combination associated with the PC. So for example, if I go here, suppose I have a set of principal components like this. So I have 4 variables here. So y1, y2, y3, sepal length, sepal width, petal length, petal width, they are the variables. So what happens now, if I have a look at the first principal component, that is y1, I cannot name it, understood? Probably you'll be able to name it later on. See, for example, if I see the loadings, the coefficients happen to be 0.3613 and yeah, so it happens to be 0.3613 minus 0.0845 and 0.8567, 0.3582, 0.3582. So here the largest coefficient happens to be 0.8567. So what I can say now, the first principal component y1 has highest correlation between the petal width. The correlation between the first variable and the third variable, petal length, that is a printing mistake. So they have maximum correlation. Similarly, when I go to the second principal component, the second principal component has a high correlation between the sepal length. So correlation between the second principal component and the sepal length is high when compared to, I'm sorry, I made a small mistake. It is 0.7301. So the second principal component and the sepal width have high correlation. And similarly, when I go for the third principal component, the highest correlation happens to be between the second variable sepal width and that one. That will happen. Don't think that we'll be able to eliminate one by one. So it all depends on the relative role. So like this, we'll be able to gauge the amount of correlation between the newly created features and the original features. So that is the beauty. Now what happens now, as I was mentioning something like this. So in sociological studies, whenever they perform factor analysis, they seek the help of PCAs. They identify for those variables what are the variables having high correlation with a particular feature. Understood? Based on that, they name it. So examples of this kind you can see in a very famous book by Johnson and Wicken. So the multivariate analysis by Johnson and Wicken will help you to get a good idea about how do we name the factors, etc. So these are the three technical points which I wanted to tell about. The principal component. So one is some of the variances will be retained, and the generalized variance will also be retained. And the notable feature is those coefficients of those linear combinations will help you to measure or quantify the amount of correlation. So basically, another point is if you have a look at the creation of the principal components, you are basically multiplying a matrix by those variables. So you are creating a rotation of the original coordinate system. So you are creating a new coordinate system by means of a kind of orthogonal rotation. So this is what we have. Now I go to the dimension reduction. So 1 minute. Now I have to, Vishwanath, please remind me after half an hour because I should not spend much time on this one. So dimension reduction means what? Dimension reduction is achieved by retaining the first few principal components by proceeding as follows. So if there are, for example, 10 variables, then in the original feature space, now you decide how many components you have to be retained. That means what? You have to decide what should be, what is a reasonable reduced dimension space. Suppose you have 10 columns there, in the reduced space, how many columns we have to retain? So that we have to decide. How that is decided will be decided by my further discussion with I will do within another few minutes. So we have to reduce the dimension. This we can do with the help of inspecting the cumulative percentage of variance, or we go for scree plot also. And sometimes there are some softwares which I cannot say bluntly that Python has no package or R has no package to. As far as I know, Joliffe cutoff value I could not find. Earlier I was using, yesterday I was mentioning to Dr. Vishwanath also, I was using one package on software called the PAST. That used to give a cutoff value called Joliffe cutoff value. That value, if possible, you can also create a small package. That is the beauty. So in R and Python, you can create your own packages to help the fellow researchers to grow further. Okay. So what happens? So if the dimension of the reduced space is R, then the reduced dimensional data matrix will be n cross R. So originally we had an n cross P data matrix. So once you decide to retain R features in the new space, then you will have an n cross R matrix. So how do we find, here only I'm missing my surface. So how do you find the ith row? So we take the ith row is nothing but the product of the ith row of the original data. Product of the ith row of the original data, that which is a vector of order 1 cross P, and the P cross R matrix whose columns are the loadings corresponding to the first RPCs. Okay, so basically, see what happens now. See, suppose, let me have a small look at this data. See, this is what I have. So here I have my PCS. So here I have my PCS. So here I have Y1, Y2, Y3, Y4. now I have sepal length, sepal width, petal width, petal length, and the petal width. So here I can create a kind of a 4 cross 4 matrix. So this 4 cross 4 matrix I have. Now suppose now I have a set of values incoming. So now those 4, I'm going to ignore some of them. That is what I'm going to say. Suppose we have 150 cross 4 matrix. That is the original data matrix. Now the reduced data matrix will be of order 150 cross 2 or 150 cross 1 or 150 cross 3. So how do I get it? I multiply that 150 cross 4. So I take one particular row, 1 cross 4, 1 cross p vector will be multiplied by that P cross R matrix. So some columns will be omitted, and as a result of that, I'll be getting my N cross R matrix. When I use the software, you'll be able to understand clearly. So this is what we do. So first, whenever we want to perform PCA, you have to decide the number of components to be retained, etc., etc. Now I'm going to tell you how we are going to do this one. Now, see here. Now I'm going a little further. So I would like to know. I would like to spend a few minutes on what are the packages available in Python. So in Python, it's made up of a lot of packages. In my opinion, it is not as user-friendly as R. In R, you can just like that play, but here you have to be very, very cautious. Even for small statistical calculations also, we'll have to make use of those packages like SciPy or NumPy or whatever it may be. So the 4 packages which I'll be using in the remaining 30 minutes are NumPy, SciPy, and SciPy, Pandas, and sklearn. So I'll just briefly have mentioned about what is NumPy. So NumPy is a package. So NumPy is a package meant for performing numerical calculations. So it is mainly used for doing a kind of sorting, indexing, and performing elementary calculations, etc. So that is what we do with the help of the NumPy package. I'll be illustrating the usage a little later. So then we have SciPy. SciPy is more popular than your NumPy. Understood? In fact, it is built on NumPy only. So it has a lot of extra features for performing interesting calculations. Then we have the most famous package called Pandas. Pandas is meant for dealing with the panel data. That means Pandas is one of the most popular Python libraries. Now I can compare this Pandas. I won't tell you can compare dplyr with Pandas. So in fact, I will say Pandas is highly powerful when compared to dplyr. So in R, we have a package called dplyr. So that package helps us to deal with the data frames. So you can perform SQL type manipulations using a dplyr. So almost all you can do using Pandas, but in fact it is more versatile when compared to Pandas. So it helps us to do data visualization, beautiful visualizations we can create with the minimum effort. Understood? So you can perform really high-level statistical calculations we can do, and we can perform a lot of machine learning tasks. Particularly for, instead of Pandas, I will recommend sklearn. Scikit-learn is a better package than this one. So that is mainly meant for performing machine learning exercises. So these are the things we have. Now I'm going to tell you. Now just I'll give you a feel of how do we work with the Pandas. See now I have there is it is a freely available software. You have, if you go to the site called Anaconda. So you have what is you come across once you complete the installation. Normally you used to do 64-bit installation. So you can install Anaconda. Now if you just I have kept it on the desktop. So once I start that application, you will be able to see Anaconda coming out. So I'll just continue to take 1 or 2 minutes, not minutes, or a few minutes, some 15 seconds or something like that. So yeah, so yeah, really disturbing. Yeah, so now once I start, you will be able to see the Anaconda navigator here, and here we have a lot of tools like one cmd.exe prompt we have, one we have Jupyter Lab, then we have Jupyter Notebook, then we have Spider, etc., etc. So many things are there. In fact, there will be a component for RStudio also. Don't bother about that. Now, I am going to use for this session this Jupyter Notebook. So Jupyter Notebook is highly useful utility which we can use for getting Python executed. See, before this Anaconda came into existence, we used to struggle a lot. We'll be always working on the command prompts. It will be very always irritating to install the packages, lot of dependents, so many complications we had. Now, once it has come out, our life has become very comfortable. Okay, so this is what I wanted to tell about. So just if you want to get a Python library executed for processing your data, simply install your Anaconda. You'll be able to get this. I think questions we can reserve towards the end. Am I correct, Viswanathan? Yeah. Okay. So, Murugesan, you please keep your question for discussion time. Okay. Yeah. So now, so once I launch this Jupyter Notebook, depending on your settings, you can start your browser. So you can start your browser. In fact, I have already opened because sometimes it takes more time. So always, so I'll be able to get something like this. So I'll get the home page. So I'll get the home page here. Yeah. So once you start here, you can see what are the available things. Okay. So this Jupyter Notebook will get activated. Now, if you want to create a coding, so for example, you go for new, take your Python 3. So if you take a new Python 3, the browser will open and you will see a lot of cells. So here you have a lot of cells. So in these cells, you can just keep typing. It is just like a kind of interpreter. So just place your commands and get it executed. So this is how we make use of the Jupyter Notebook. Now, one biggest advantage of using a Jupyter Notebook is, see, for example, I'm going to use already have created a notebook. So this is called Jupyter Notebook. So this is the biggest advantage. Now, what we can do now, see, not only running the program has become comfortable, even teaching has also become very easy once this notebook provision is available. So with the help of Jupyter Notebook, you can create a notebooks which you can keep it ready and you can get them executed as and when you like. So now I have PCA using pandas. So PCA using pandas is a caption I have created. So this is for my understanding. So it is not see, for example, if you want to create such no, I don't want to deviate from that. So how do we create such captions? Just you go here, if you take markdown and if you start with one hash, it will start creating. So now it has changed. So if I go back to markdown, so it gives like this. Now if I run this, that caption will be created. I don't want to spend much time on that. Now I'm going to tell you how to bring a particular data into R. Now I'm going to, sorry, not R, I'm sorry. I have been using R for several years. So again and again, that R comes to my attention. So, so if you want to get some code executed, so I go for something like this. So always, even for small things, understood, you'll have to depend heavily on the packages. So now what I have done, I have decided to make use of a pandas. So pandas is a package which I'm going to use. So I'm going to use the pandas package for reading the data and performing something more using the data. So what I do now is the command import pandas as PD. So PD is your one creation. You can do anything of your choice. You can give PDA or PN. It is left to your personal use. But invariably, I have seen people using PD for pandas. So it is only for our reference. We create an alias. So import pandas as PD is one command which I have used. Then I have used import OS also. Import OS means so that is operating system. So with the help of import OS, you'll be able to get your current working directory. You can do all kinds. You can make all kinds of changes. Everything you can do. So then I wanted to know where I am placed. So just when I execute this, now if you want, you can do one thing. Now I have created and I have kept all my outputs here. So it is very useful. See what I can do now. I can go to kernel. Now what I can do now, I can restart and clear all outputs. This is really irritating. People coming and going. So if I give a restart and a clear output, everything will disappear. So whatever outputs you are seeing here will go away. So it will take a few minutes. So now I have only the notebook with the commands already I have created. Because see, normally it is not my practice to keep the commands ready. Normally I used to write coding in front of the audience, but being a large gathering, I did not want to take any risk. Naturally, whenever we write our coding, we often make syntax mistakes, sometimes even logical errors also. So to maintain the smooth flow of the lecture, I have done that. So now you must have noticed here. Now what happened? So this is C. So after the execution, I have seen this. Now, just for my understanding, so just I wanted to keep you informed, how do I read it? So for reading the data from a data frame, so it is like a data matrix. So a data matrix is often here, we store it in the form of a data frame. So if I want to read a data frame, I have to make use of a particular instance of pandas. So PD is the name I have set for pandas. So I have used PD dot. So that period is very important. Read underscore SV. Read underscore SV is a built-in function available within pandas. So read underscore CSV, and inside I have written the name of the file along with the path. Please remember, you'll be using forward stroke instead of backward stroke. So whatever you have read will be transformed to this HSB. So the read output will be taken to that HSB. Now, once I complete this part, now I am placing my cell here. Now what happens? Now, if I just execute HSB, I'll be able to see the content. So I'll be able to see the content. So this is what I had in my HSB. So this is the file which I have kept in the in my folder where I have shown you the path. So that HSB folder comes here. So that HSB folder comes here. So it says you have, see here, one thing is the index will start from 0. That is one thing. It is not like R, where the index starts from 1 to 200. So this read underscore CSV is something which you can compare with the read.csv in R. So in R, we have the flexibility of choosing the file dynamically. Once that function is executed, you can locate the path by using those directory list box, etc. So that is, as far as I know, it is not there. So you have to completely give the path. So once the reading is completed, you come out with this HSB. Now this this head, tail, and all just like our R only. So what happens now? HSB.head is it will give you the first few rows of your HSB. So here it gives you the first 5 rows of my HSB data frame. Similarly, if I want to see the last 5, I'll be seeing my if I can execute my HSB.tail. So if I execute my HSB.tail by running this, I'll be seeing the last 5 columns. So this is what this is how we import the data from your data frame and keep playing. But remember, one thing which I have seen is people use this PCA for categorical data. That is very, very dangerous. The principal components which I discuss here is specifically meant for dealing with interval value data. That is for continuous data only, you have to use this one. But even if you use the same functions after doing a kind of a coding, it will work. But strong theoreticians will not accept your findings if you make use of this PCA for categorical or nominal data or whatever it may be. No, okay. So you have to be very cautious. So we have one. In fact, there is a package also called a CAT PCA, which is used for performing principal component analysis for categorical data. So this is what I have done. So I have shown you how to import the data and how to see the contents. If you want to, you can see the entire content, or if you want, you can see a part of the data frame, etc., etc. That is more than okay. Now, if I want to perform the PCA for this data, deliberately I have taken this data because I wanted to get you familiar with how do we do slicing. So slicing means what? Taking a particular portion of the data frame is what we mean by slicing. So if you want to select the first 5 rows, if you want to select the first 5 rows, what I am suggesting you to do now, first 5 rows, yeah, so I'll go here, just I'll run this, when I run this, I'll be able to see the first 5 rows. So HSB square bracket 0:5. That will give you the first 5 rows. If you put 0:10, it will give you the first 10 rows, etc. So remember, the first one starts with a 0. So totally you will get 5 rows. Last index will be 4. Now sometimes we'll be interested in seeing rows as well as columns. So for that I have given HSB iLook. See, there are 2 ways of locating the data frame. One is just ordinary LOC, like what I have given in below, and the next one is integer location. So I go here and this is very irritating. So I go there. So when I use this one, I'll be able to see the first 3 rows and the 4 columns. First 3 rows and the 4 columns I have. So I go below this. So here I have LOC of this one. So if you want to see specific rows with all the columns, so I can do like this. So it goes like that. Now, what is more important now? See, as I told a few minutes back, if you want to perform PCA, you'll have to use only the numeric data. How do I use the numeric data? I take so I cannot use the entire data frame. I have to throw away the first few columns. The first few columns contain categorical data. So I have to retain only the last 5 columns. So I have decided to use the last 5 columns by using iLook function like this. iLook, if I leave the space before colon, that means I am trying to extract all the rows. I am trying to extract all the rows, but only the last 5 columns. 5:10 means what? So it will start from the 6th one and it will go up to the 10th one. So it goes like that. So once I execute this, I'll be able to get the last 5 columns. So the last 5 columns have come here. The same thing we could have done like this also. So HSB, what I have shown earlier is same as this one. Now let me come back to this. So I'm not interested. Skip some executions also, provided what is there in the execution is not needed for further calculations. So I have done like this. So then also if I make a call like this, ht.var, so I'm getting all the variances. So all the variances I'm getting. So I had in my HD, what did I have? I had 5 variables. So for all the 5 variables, I have the variances. So some of these variances, if you want, you can get it. I'm not going to spend much time because already it is 10:43. So some of the variances you can get it. So what happens now, if you add the variances of those principal components, that will be same as these things. Okay, so this is what I wanted to tell. Then I'm going to show you how to get the covariance also. So I am getting my covariance matrix. So I have my covariance matrix like this. So naturally, when I have 5 rows, the covariance matrix will be a 5 cross 5 matrix. So I have the variances like this. So variance of read is 105. This is what we have seen. For example, variance of social studies is 115. So that comes here. So the covariances are here. Then I go for my correlation. So when I go for my correlation, I get the correlation matrix like this. This is not very much needed. Anyway, just I wanted to say this. Okay, now comes the question of getting the principal components. So now let me summarize what I have done. Just I have told you, if you want to perform PCA, you make sure that you are importing pandas by setting an alias. For example, I have used PD. And after that, its role is there. But if you want to proceed further, suppose you want to perform a principal component analysis, you have to depend on another library also. This is the most popular library we have in Python. So there's a scikit-learn. See, the sklearn is if you want, you could have got from, you could have imported sklearn like this, import sklearn as sk, and then you could have accessed decomposition, then you could have gone for PCA, etc. Just to avoid a waste of time, I have put everything. So this is another way of this one. So what do I do now? I have my package is sklearn.decomposition. So I have gone into there. Now, inside every package, like what we have in R, we have a lot of functions. So one function which we have is PCA. So PCA is the built-in function available in sklearn.decomposition, and I have imported that. So what happens now? This PCA is made available. So once this is successfully executed, the PCA function which resides in sklearn.decomposition is freely available. Now you can make use of it. So what happens now? What do I do here? I make a call like this. PCA is my function staying in sklearn.decomposition. I call that function by passing only one argument. See, there are a lot of variations you can do in plenty of ways. The simplest ways only I am explaining. So just to mention the number of components. So you tell how many components are to be retained. Now, since I had a very small data set consisting of only 5 features, I have decided to perform PCA for all the 5. So I wanted to get all the 5 principal components. So once I complete this, I have with me my PCA object. So that it is a kind of machine which you have said. So once the PCA, the big PCA n component, this small PCA is your name. You can give any name of your choice. For example, you can call this as a PRN, PRC, or whatever it may be. So it is your user-defined quantity only. That PCA n this we cannot change. Whatever you have, so you have done PCA. Then what you are going to do now? You are going to fit the data. See, the data which I have read is in the name of HD. So HD is the data frame which contains the data. Now what I am instructing that machine to do. So it is, I am asking it to fit that PCA. So this is a general working, a framework we have created for getting 5 components. So that I am going to apply for my HD data frame. So once I apply this, I have it been, so it has performed. So once you get this, see the details regarding this V10, etc., you can get it from websites. See, for example, there is a website developed by scikit-learn itself. There you can get complete explanation about what are the meanings of all these things. Okay, so here basically it performs what is known as a singular value decomposition, not like a eigenvalue decomposition. So here it performs singular value decomposition, and it has created. So now you can ask me, where are the principal components? Where are the principal components? So the principal components are here. So the principal components are here. So if you want to display the components, just you give run. So if you give run, you'll get those principal components. So you'll get those principal components. Have you understood? Now suppose I have used only 3. For example, if I use 3 here, let us see what happens. Now I'll go here and I'll come here. When I come, it will show only 3. Understood? So earlier it was showing 5 principal components. Since I'm asking it to fit only for 3 components, it is giving me 3. But still I don't want to disturb my preparation. So I have performed once again. Now you can ask me, where is that fee? That will come only when you execute this one. So PCA.components will give you this one. So these are the loadings which I have shown in my earlier slide. In the PowerPoint slide, I have shown, y1 is equal to this one, y1 is equal to something into sepal length, petal length, etc., etc. So those loadings are available here. Now these loadings you can give interpretation. So what I have done, I have completed the development of the loadings. So I have, if you are very much interested, I can just show you. I have come up to this. I have come up to this. So I have come up to this. So I'm sorry. So I have come up to this. So here we have PC1, PC2, PC3, P4. Here you have column wise. It is this is the output which I got from R. So now you can make use of these coefficients and build your principal components. So you can make use of those coefficients and build your principal components. That is what we have. But what is your original data frame? Original data frame is 200 cross 5. See, even though I said 200 cross 10, I have sliced and retained only the numeric part of the data frame. So the first 5 columns are kept, and so as a result of that, my original feature space will be a 5-dimensional feature space. Now, you don't worry about this. This is not needed, just for some cosmetic work I have done. Without that also, I could have created the data frame. Now, what I am going to do now, very, very important, please listen. I said, original space will be 200 cross 5 means the new feature space will also be 200 cross 5. So that 200 cross 5, how do I get it? How do I get the 200 cross 5? No, just I go for PCA.transform HD. PCA.transform HD. That means that HD data is sent to a function called transform. So that transform function will give you the new feature space value, so that newly created 200 cross 5 matrix you can get it, but I think it is better to show how it works. So this PCA.transform HD is performed, so it goes like this. So here we have data frame. So here we have 200 cross 5 matrix. So what happens now? See here, when I call PCA.transform HD, that fellow is throwing as output, it is throwing as output an array. But remember, an array is different from a data frame. So what happens? This data frame, see, if you want to explore further, you will have to convert this array into data frame. Now I'll talk a bit slowly. Just I'll spend a few minutes. What I have done, I have imported the data. I have imported the data, and I have imported the data, and I have extracted only the numerical part. That is what I have done up to this point. That is what I have done up to this point. There is no need to see the covariance matrix and all. Just I wanted to show you how Python behaves. Then what I have done, here comes the important point. See, performing PCA is very, very, very simple. Just import the data frame, import this PCA, import PCA from this sklearn.component. So import the PCA. Now PCA is available. Now you call that PCA function and you store that mechanism under the name PCA. Now this small PCA we can use for fitting. So if you want to retain, say suppose we have 64 variables. Now if you want to retain only 30 of them, you keep that 30 here. Now a newly created feature space consisting of the reduced number of dimensions will be obtained like this, PCA.fit. That is available. Then if you want to see the components, just we make this. These are the only 3 important things. One is calling PCA function, then fitting, then seeing this PCA.components. Now what happens now? This PCA.components is unfortunately giving you an array. See, it is better to have this kind of a matrix rather than seeing an array. Now, if you want, you can convert an array into a matrix just by performing a small thing. See, for example, I'll just put it like this. Just I would like to create one cell. So just you go for insert and create one cell above. Now what I will do now, I'll call this as PDF, some PC data frame, something like that. I will have. I'll call it here. Now what will happen now? So I'll have PD dot data frame, PD dot data frame, PD dot data frame, and whatever I got there. So this what is the name of that? So PCA.transform HD. If you put there, not that one, components. If you put there, like what I have done here, that fellow will convert that into a matrix. So that is what happens. So this I'll show you in the next illustration. I have given that conversion. I don't want to do any adventure here. So now we have converted PD.data frame is equal to this one. Now, for example, see, I can make it comment. Yeah, I'm sorry. Just 1 minute. I'll make it a comment and I'll show you. This we can skip if you want, but I would like to retain this. I'll take away these fellows. I'll take away these fellows. Why? If I take away these fellows, what will happen? No. Then I will display my df underscore PCA. Now let me show you what happens. This is the columns. Yeah, this is the dangerous thing which I don't want to do. Let me undo everything. So let me put it like this. So let me come here. Let me go back to this. So let me go to this and run this part. So once I run that, I'm able to create. See what I have done now. It is creating an index, and here I am giving the names like this: 0, 1, 2, 3, 4, 5, etc. So So here I have the newly created future space. So this is the newly created future space. Now comes the question: how many components we have to keep? So if I ask for how much variation is covered, you can ask for PCA.explained variance ratio. So if I ask that, that fellow will give me how much. See, the first PCA covers 67% variance. First PCA covers 67% variance. The second principal component covers 11% variance. Remember my statement. if you consider the variances of those PCAs, you can order them. The first PCA will have the largest variance, like what I told. Next will have the next largest. Next will have the next largest. So like this it will have. Then what we have to do now, you can see, you have to decide how much variance you would like to retain. Suppose you have decided to retain 80%, whatever it may be, just you make, see for example, if I want to know what is the total percentage explained here, what I will do now, I'll take that 67 plus 11, something roughly 78. 78 is divided by the sum of these things will give me the percentage variance covered here. That is also converted here. So I have converted this PCA dot explained variance also. All these scripts we can understand. So I'm going to give you a kind of a plot here. So I'm going to run this. When I run this, yeah. Now I am getting what is known as a screen plot. So this is a plot which I have created. This is the coding you can share. So anyway, the recording will be there. Any point of time you can just experiment. So here what happens? NP.round means the variances. See, we had there something like 68, 67. That is illustrated here. Next one is having 11. So that comes here. So those heights are given here. That is what we do here. So here I take my height as the percentage variance converted here. So here we have we are setting some labels. That's all. So we are setting some labels. Okay. So all is there. So the general rule is you just decide how much variance you want to retain and then do it. Then if I go here, I am just going to decide how much I have to retain. So what do I do now? I have to accumulate. So I have this cum sum is a function available in Python that will accumulate the variances. So the explained variances are accumulated. So finally to go up to 1, that means 100% accumulation is there. General rule is you see the point at which this curve becomes flat. That means it is tending towards, appearing towards parallel to the horizontal axis. That is the point at which you have to keep. So then you keep this. Then suppose after inspecting this dendrogram, if you see only 2 variables are to be retained, just you give this, so it will give you a plot of this one. So this is how we perform a PCA. Now for a change, I am giving you one more demo also. After that, we'll start our question session. So here I have one data set. So here I have a very popular data set which we use in machine learning. So this is called digits data set, which is inbuilt. Like in R, here also we have a lot of data sets within Python. So this is the general syntax we use for loading the data sets. So from sklearn, I am importing the data sets. So that is a general thing. So from the data sets, I am loading a package data set called digits. Like iris, we can have something like this. So I have loaded. So once I load that, I'm asking what is it. So it is generally we use this. Whenever we have confusion, we will see what we have here. So it says the type is sklearn.utils.bunch. So it has bunched the data with the target, So see, like what is the target now? If you see the iris data set, you have 5 columns. The 4 columns are data, and the 5th column happens to be a classification variable. So like that, the class is nothing but your target. Then I take separately X, because the target should not be involved in performing PCA. Target should not be involved in performing PCA. So I just go to this. I think it is very irritating to see these people entering. So I am just seeing the shape. Shape is so I have come up to this. Now I am executing this one. Now it has 1,797 rows. Prakash, you have to control these fellows. Okay, so yeah, just a minute.
Shall we lock the meeting? Lock the meeting, sir.
Please do, sir. It is really causing a lot of distraction.
Okay, I will lock the meeting. Nobody can enter.
Thank you, sir. I have removed that fellow. Yeah. So now what happens now? I have with me the data frame that is an array. So it is not like now here it is not like an ordinary data set. Here you have 1,797 instances and 64 columns. That means you have 64 features. Now, what do I do? Just to see what I have done. Just I am repeating quickly. So here we have PCA 64. So that means what? The number of components I want to retain is 64. No need to explicitly state. So once I do that, the result goes there. Then what do I do? Simply you go for PCA.fit transform the data. That will give you the projected data. There you can get it. So I'll just run it. So I have projected. So like what I have done in the earlier instance, I have completed the cumulative sum and I have gone there. Now you can see here, this is a better script plot. So it goes like, then you can ask me, why did you take that one? Because that gave me an opportunity to introduce the slicing and so on. So now you can see this plot, it is somewhere here you can stop. So here it is trying to be parallel to the horizontal axis. For example, instead of 30, you can have 20. It is your description only, 10. So in fact, it is better to go through the percentage of variances covered also, that we can get from like what I have done earlier, explained variance ratio, you can inspect and get it. So this is what we do. So we get this. Then what do I do here? If I want the first principal component alone, I can get a comma 0, comma 1. So like this, just I am running out of time. So I have plotted this. I have gone beyond this. So the first principal component and second principal component I have plotted. And here, now what I have done now, see, originally we had 64 columns. I said in the transformed space also you have 64. Now suppose I have decided to you retain only 11 features. What I can do now, I can extract, I can do slicing by having a pd.data frame. This is something which I have already explained. So put it like this, x is equal to pd. This is what I was trying to do. Understood? So it comes like this. Now I am showing you the head. That means what? So the reduced future space is shown here. So it comes there. So this is how we perform a dimension reduction. So reduced space is there. So after this is common for everything. See, PCA we use for machine learning, we use for regression, we use for factor analysis, etc., etc. Whatever you want to do, that is different. Irrespective of what you are going to do, this is up to this you have to do. So sklearn depend. So get the PCA function, go for iterations, see a plot, the script plot, and if possible the cumulative percentage also, and decide how many components you have to retain. And this is the part which we will be using. Okay, now beyond this you have to do. Now in machine learning we have a technique called the KNN classifier. Now what I have done now, I have decided to make use of the newly created dimension space, and I want to use, for those who are familiar with the KNN will know, we will have one set called training set and another called test set and a classifier. So when I develop the machine, I call knn.fit. Knn.fit is the classifier which I have defined. Understood? When I call this, I'll be getting a classifier. So it has performed the classifier. Then if I want to predict, what I have to call, I have the machine's name is KNN. So if I call knn.predict, now here I have sent the entire training data set for the purpose of prediction. So I have sent that and I got the output. See, Python is really fast. Based on my experience, I can tell you it is really fast than this one. So I go here, then we have one more component like the metrics that gives me the accuracy. And here I have, instead of passing the entire data set, I have passed only the 15 instances in a reduced space. And I have run this and I have taken those 15 instances. I have used those 15 instances alone for the purpose of prediction. So the prediction happens to be 0, and these are the predicted classes. See, actually this data is something like this. They had about 1,001, they had about 1,797 images of the digits 0, 1, 2, 3, 4. Understood? So those images were stored in the form of 8 by 8 pixels. So 8 rows and 8 columns. That is why how you get that 64. So that large data set is reduced to very small data set, and I have used only the 15 instances here. I have just extracted in the reduction dimension space 51. For them, the predicted class, the first image is 0, second is 1, third is 2. So like these are the predicted digits. So these are the actual digits. So you can just have a comparison. So any classifier will work very well provided the accuracy is more. So this is what I wanted to share with you. In fact, I have two more demos also for illustrating how do we perform PCA regression, etc. So for want of time, because already Dr. Viswanathan has advised me not to go, because normally, based on my experience, these kind of lectures should be given at least 2 hours. Then only both the participants as well as the resource person will have satisfaction. So within the short span, I think it is enough. Okay, Dr. Viswanathan, I think already have crossed 5 minutes, more than what I was allotted. So if you wish, I will stop and entertain some questions. Yeah, somebody was, unmute yourself. Yeah, now you can talk. Yes, Dr. Viswanathan.
Sir, you can proceed for a little bit, and we can enter into the question answer session if it is not hindering the flow, because ultimately, as you mentioned, this has to be taken care. It should reach the ultimate end user.
Yeah. See, one thing which I wanted to tell you is for the principal components, I have given some uses. In fact, this is what I had in my mind. See, this PCA, basically it is a dimension reduction technique. A small request to Dr. Viswanathan. The host should control the entry of people. That is really causing a lot of irritation. Okay, that is one thing.
Yeah, I thought the co-host would get the rights, but I am not able to communicate. That is the issue.
No,
sorry, very sorry.
Yeah, no problem. See, and one more thing. See, I said basically it is dimension reduction. Now that you can do wherever you want. For example, as I have shown a little while ago, you can use for classification like the KNN. You can build trees. You can perform clustering. You can do SVM. Whatever you want, you can do it. Okay. And being a large gathering here, I wanted to spend some time. See, this PCA is indirectly helpful for even detecting the multicollinearity also. So multicollinearity detection can also be done with the help of PCA. So what happens now? Basically, if you see the presence of multicollinearity, we notice by seeing the rank or the determinant value of that X transpose X. If it is nearly singular, what happens? It is possible to have multicollinearity. Am I correct? Yeah. So what happens now? See, when you perform PCA, when you get the variances, as I have told earlier, that was the idea. So when you get the variances of those principal components, in fact, I have not. Yeah, the accumulated. I think I have shown you the variances. I think I have shown you the variances. So here you can see the variances. Can you see the screen?
Yes, sir, we can see. And
so here, you have a very small height here indicates the presence of multicollinearity. Understood? So smaller variances, because remember, the dispersion matrix of your PCA will be your diagonal matrix. Am I correct? So the determinant value will be the product of the diagonal entries. So if some PCAs, particularly PCAs of higher order, have smaller variances, it is most likely that your determinant may become 0. So that is also a kind of, what can I say, symptom of the presence of multicollinearity. So a very smaller variance for your PCA gives an indication for the presence of multicollinearity. In fact, I think I have taken one data from our very famous book. I don't want to go for the description of the data set. You can see in Montgomery, that is a beautiful, yeah. So see, as I told earlier, I lost my memory power. So I have one notebook called PCA regression. So I think I can just open it. Yeah, I can just open it. PCA regression, open. See, this is a very beautiful this thing. What can I say? Yeah, so PCA regression, I think last modified. Still those fellows are entering. Yeah, PCA regression, yeah, Montgomery data. So this is the notebook which I have here. So this is a data set. This is, I call that as belly.csv. So this is a data frame. I don't want to run and show you. This is a data set consisting of one response variable, namely y, and 7 regressors. We had 7 regressors here. Now, just like what I have done. So here, this is one more thing. See, in SK, in scikit learning, you have a lot of components. I have used earlier decomposition. So you have pre-processing is also. Lot of pre-processing tools are available in this SK. See, in fact, I have done only scale. In fact, variety. So this is one advantage of using Python. So even though R is very easy to use, it is not as powerful as Python. So if you simply call scale, I have some examples which I was using in one of my earlier classes for explaining various types of scaling. So this is our usual standard scaling I have done. So I have done the scaling and I have converted that array. See, once you do scaling, the scaled function will give you an array, not a data frame. So as this is what I was trying to do. I converted that into a data frame and I have shown this now, and I have extracted, I have considered, I have just shown you all the scaled values. So here I have the variances, then I went for covariances, then I have performed a PCA. Now when I plotted, because here you can see here, see it is very, very small. That means you have reason to believe the data is suffering from a multicollinearity. So this is what I wanted to tell. So this is one thing, and probably instead of 10, you can retain 3 or 4 variables. So like this, we can reduce dimension. And what I have done now, I have decided to use only 3. So I have decided to use only 3 response variables. Remember, these response variables are not the original regression. I'm sorry. 3 regressors. I have decided to use 3 regressors, but these 3 regressors are not your original regressors. They are the regressors defined on the original space. So this 3. This PCA 0 is 1. First y1. This PCA 1 is y2, and this PCA 2 is y3. So the artificially created response variables are used for the purpose of creating. So then I went back to that response variable also. Then I have fit the linear regression model, fit the regression model. I got the regression score, all this. So these are the coefficients. So I had 3 regressors. So the regression coefficients happens to this one. And in fact, it is also highly insignificant. Probably the second, I think 1 is enough, whatever it may be. So this is how we can do PCA regression also. This is only an illustration purpose. So this is the second thing which I wanted to share with you. And the third one is, which this will be my last item. The third one is, see here, when I performed the PCA, it was making use of singular value decomposition. It was making use of a singular value decomposition. In fact, if you, based on my observation, I may be, normally these kind of observations I don't make just like that. Now, if you do eigenvalue decomposition also, you're almost getting the same answer. That is what I have yesterday performed. Just I was very curious because in R it performs singular value, in R it performs eigenvalue decomposition. So just I wanted to see whether there is any difference. So this is the code which I have run. So I could see it is not giving any significant different result. So it is almost giving. So the iris data set is also available in sklearn itself. So this I have done. So the data target, all those nonsense you can understand. Shape I have been showing. So everything I am showing here. So now what I want to notice here now. See here, these are the components and these are the explained variance ratios. These are the explained variance ratios. Then I went for the eigenvalues. So the eigenvalues are almost the same as what we got earlier. So almost the same as what we got earlier. So it goes like that. So I think with this, I would like to stop because anything too much is will become very boring. So I would like to close my session. If you have any questions, feel free to ask. Dr. Viswanathan, can you hear me?
Yeah, sure, sir. Sure, sir. We are expecting the questions from the audience, and we will filter it. And
yeah.
Sure.
Good morning, Dr. Emmaris. Good morning, sir.
Sir, Vishwanathan sir, are you summarizing the chat questions, or are you going
No,
to?
I am not. I am not able to see the chat questions.
No, okay, sir. Then I will release the chat also, sir. Now.
Yeah. I will select a few. Thank you, sir.
Then, if meantime, if any participant wants to interact,
Yeah,
with
sure.
express the raise hand option, we can ask them to unmute and speak, sir.
Okay, sir.
Now I enabled the chat also, so the questions will be poured into the chat window also. You can collect the questions and you can present, sir.
Okay.
Before that, any participants who wants to direct the interaction with the resource person, let them raise hand, sir. Then we will unmute them, sir.
Sure, sir.
Actually, we will ask them to unmute.
Hello.
Yes, sir.
I have one question.
Yes, sir, please.
Yeah, please.
Can I?
Yes, sir. Carry on. Please proceed.
Professor Sampath, I think it was a nice talk because I'm still a learner as far as Python is concerned.
Okay.
But as far as the technical part is concerned, see, I have been doing some work on this scree plot to identify the number of components required.
Yes.
But what happens is the examples which you have covered, I think the example which you have shown was the first two components covers almost 75% plus, if I am right.
Not
yeah,
all.
60.
No. So the first one was covering a little bit.
Yeah, generally, 67 plus 11, if I am right.
Let me complete. Generally, when we have a smaller dimensional feature space, the first few PC will attract maximum variance. That is what we have noticed. Suppose we have, even if you take some iris data set, the first PC itself will swallow the maximum information in that. So that will happen when you have lower dimensional space. But we have feature space like what I have shown earlier, that digits data set where we had 64 features, the coverage will not be so high.
Yeah, but my question is, if it is going to be something like this, then I think your problem of looking at the scree plot will help you. But if it is going to be a sort of an even thing spread out, how will you decide about the components? Like I can say 40, 40, 35, 35, 25, so on and so forth. How will you go about?
Okay, 1 minute. How many variables? See, suppose you have, suppose 5 features. Let me not get analogy. Okay, if all the 5 have same amount, like 20, 20, 20, etc. No need to be a PCA because they themselves are independent.
No. I'm not saying all of them. I'm not saying all of them.
Okay.
But few of them, but all of them are going to be closer to each other. Do you have to use some objectivity there, or you have to use only the tool itself?
No. If all of them are almost equal, then you have reason to believe the original coordinate system itself is made up of independent axes. So in such cases, going for PCA will be highly dangerous.
Yeah, that's right. If all the 5, I am not saying all the 5, but the first 3, let us say, are going to be closer, but not like 67 and 11.
So
it is going to be.
You retain all the 3.
So your point is it has nothing to do with the question of one is very high and the other is low. You have to look at the cumulative value. Am I right?
No. You have to. We go by only the cumulated value. See, like what I have shown in the digits case. For example, I'll just show you that scree plot. Digits. So if you have a look at this plot, see here. In this plot.
The neck.
7 minutes. The plot is somewhat like this. Now you can see here, it is climbing up. So up to 10, between up to 15, it is climbing up. So here, the rate of increase is not much. So what we'll do now, we'll keep a threshold. We'll decide a threshold at the point at which we have to close. So in my opinion, I can tell, for example, something like this will be enough. But added to that, you see what is the cumulative percentage covered by that one also. That is also important. So for example, if I put a vertical line here, so it covers 80% of the variance. Am I right?
Right.
So nothing prevents us from retaining the first 10 PCS. So in fact, that is what I have done towards the end. When I introduced my KNN classifier, I have used 15 features, if I am correct. 15, not this is 15 instances. I think in the PCA I have used how many instances I have. You can project anything you want. Then I have taken the number of neighbors as 10. But what is my X? X happen to be original feature space. So I think I have taken something like 11. So that means 10. So 10 features I have retained. So this 0 indicates the first feature, 9 indicates the 10th feature. So retain those 10 features and perform KNN classification. So the KNN classification, which is supposed to be one of the inferior classifier, gave me an accuracy like 0.97. So this is what happened. So the number of components which we have to retain, generally we don't blindly go by scree plot alone. We see the cumulative percentage covered by that also. But most of the times it was. But in my opinion, personally, it is my interest. As far as I know, it is very dangerous to make statements as if we are a big shot. Joliffe cutoff is better than these fellows. Understood? These are all kind of naive guidance only. Joliffe cutoff will be the most scientific one. In fact, Dr. Viswanathan was telling one more thing yesterday. So in fact, one more thing which I want to tell is, I suggested scaling. So the scaling will also an effect. The way in which you scale the data is also there. In fact, not only that, I have another example also which contains missing values. How do you account for missing values? How do we do imputation? For imputation also, we have a lot of packages available within sklearn itself. But sklearn is a high, really I wonder, the power is beyond imagination. You have free software, throwing away so many tools is beyond imagination. So it all depends on how do you account for scaling. How do you, see the data which I took from Montgomery, it was showing only 2 without scaling. If I do scaling, it forces me to retain 4 principal components. So all those things we have to take into account. We cannot just like that push the data inside the software and reach some conclusions. That is very, very dangerous. So one thing I would like to suggest for the beginners is, first of all, you have to give room for data cleaning. First of all, you have to do account for missing values. It is not a very simple answer. I cannot tell blindly that throw away all the records with the missing values. You have to account for that. You have to decide how to mute them. So then we go for scaling also. So that we have to do. So many things are there. So it goes like that. Okay. And
thank you.
Thank you, Professor MRS. Nice to see you. Yeah.
It's a very good question, so that everybody gets highlighted with the answer. So the question as well as answer, both they should be applauded. And I think in the process of pre-processing or cleaning, even the outliers has to be taken into account, it seems.
Yeah,
Professor will agree.
One more thing. This gives me an opportunity. The PCA can be used even for outliers. By plot, how do you manage? You go by the first and the second PCA scores only. Correct?
Yeah. Okay, sir. Okay, sir.
Without proper understanding of the PCA, it is very dangerous to proceed further. Yes.
Okay. Because of thank you, sir. Thank you, sir. And because of time constraint, I think we can allow only one more question and wind it up within 5 minutes.
Sir, one Madam Rebecca is there, sir.
Yes, sir.
Yes, sir. Please.
Madam Rebecca, madam, you can unmute yourself and you can speak, madam.
Actually, in the screen, Professor's mail ID is showing, so that even if others, if they have genuine doubts, then you can directly.
Genuine doubts. Yeah.
It's mainly a matter of time now.
Yes.
Sir, I think madam is not willing. I think Viswanathan, sir, you can.
I will conclude, sir.
Chat box questions, sir. Chat box questions. If there anything, you can just tell the sir.
Sir, I am not able to see the chat box, and moreover, time is also not permitting me, so that I think it's better we can wind it up.
Okay, sir. Okay, sir. Ask you, please.
Yeah, thank you, sir. Thank you.
Dr. Viswanathan. So I would like to thank all my colleagues in the Presidency College for remembering my presence, even though I am a retired person with a very little activity. Thank you very much for inviting me to give this lecture. Thank you, one and all.
Sir, it's our immense pleasure, and it's a great opportunity that you share your knowledge with all of us. And it is from our end, we have a lot more to So thanks a lot, sir, for coming and sharing your experience and knowledge. Thank you very much, sir.
Thank you, Mary. Thank you for all.
So we had a wonderful first session on PCA using Python by Professor Sampath sir. And thank you, sir, for sharing your knowledge with us. Now we'll move on to our second session by a dynamic statistician and a scientist, retired professor and director of ICMR, Dr. P. Venkatesan sir. And I hand over this session to Professor Radha ma'am, Assistant Professor, Department of Statistics, Presidency College, Chennai. Professor Radha ma'am is there? So I request her to introduce the resource person. Professor Radha ma'am.
Sir, I'm not able to. My voice is audible?
Ah, yes, ma'am. Yes, ma'am. What about the video, ma'am?
Okay. Good morning, one and all. On behalf of, thank you, Jayashree. Good morning, one and all. On behalf of the Department of Statistics and IQAC team of Presidency College, I take immense pleasure in introducing my guide, mentor, Dr. P. Venkatesan, retired Scientist F, Senior Deputy Director, ICMR Chennai, now visiting professor of Sri Ramachandra University, advisor to Child Trust Hospital, Chennai. Sir also got his PhD degree from Madras University, and of course his diplomas from ISI Kolkata and from Bombay. And also he has got postdoctorate training in machine learning, GIS, computational biology from Brown University, Providence, Rhode Island, USA. And adding to his credit, I would like to mention few fellowships. Forgetry Fellow from Brown University, USA, Fellow of Royal Statistical Society, UK, and many more. Sir has got more than 40 plus years of teaching experience and research experience. To his credit, 15 national health surveys, visiting faculty of Brown University, USA, published in journals and also chapters in books in more than 350 scientific journals. And he has delivered more than 500 invited talk in national and international conferences. And Sir has guided 40 scholars for the award of PhD degree. And his area of research are diseases modeling, computational biology, artificial neural network, SVM, genetic algorithm, rough set, Bayesian, inference, GIS, and many more vast field. And Sir has been awarded Lifetime Achievement Award by Dr. MGR Medical University, Tamil Nadu for exemplary contribution towards medical education, and many more awards, both national and international level. Sir has visited many countries like USA, UK, Germany, Australia, Japan, Singapore, etc. He also holds many presidential position in International Biometric Society, Indian Society of Medical Statistics, and many more. Sir, it is a great pleasure and in inviting you for this second session of today's webinar. Sir will be delivering a lecture on machine learning approaches and statistical learning theory. I think this, in the current area of statistics, it will be useful to all the participants. I hope you will enjoy this session. Thank you, sir. Sir?
Madam, Sir will be joining, Madam. 1 or 2, please give 1 or 2 minutes, Madam. He will join just now. Okay, please. 1 minute. Sir is joining now. Please wait for a while.
VP லைன்ல இருக்கீங்களா?
வெங்கடேசன் பேரு. சார் உள்ள இல்ல, ஆனா உள்ள இருக்காராமா, அவர் மீட்டிங் பார்த்துட்டு தான் இருக்காராமா.
Sir, now we will ask all you to, we'll give the power to unmute generally, and now only resource person please unmute, because we are not able to find out the resource person among the audience. Okay, I will now allow all the participants to unmute, but you don't, please, others don't unmute yourself. Only the speaker has to unmute now. Yes, please, now the resource person, Dr. Venkatesan sir, please you unmute yourself and speak, sir, so that we are able to find out.
Now it is unmuted.
Yeah, thank you, sir. Thank you, sir.
Yeah, now, yeah, sir. Yeah, sir. You have come with the name of Vishalaji Sivaraman, isn't correct, sir?
Pardon?
You are come with the Dr. D.K. Veerasappa, sir. Veerasappa. What is the name?
My name. My name is Venkatesan. Venkatesan ICMR, you are given the connection.
Okay, sir.
Okay.
Name?
I think all initial problem we are sorting it out.
No, okay.
Can we start, Viswanathan? Can we start?
Yeah, please. You can.
Okay, we start.
Sir, you have come in the name of Vishnu. Sir, 1 minute.
Yeah.
You are coming in the name of Vishnu, I think, sir. I will ask you to, make a co-host, sir, now.
What is the name?
Now, I think.
You are sending the link.
Sir, now you unmute and speak, sir, please.
Unmuted. No, unmuted.
Yeah, correct, sir. You have come in the name of Vishnu, I think.
Vishnu? No, I am not Vishnu. Vishnu is other person in the afternoon. Okay. However, I am getting these. Can I share the slides?
Yes, sir. Please, sir.
Now everybody can able to see the slides?
Yes, sir. Yes, sir.
Okay. I think still it is good morning. Good morning to all of you. So first of all, thank the organizers for inviting me as one of the resource person for the workshop. And, I also thank Professor Radha for introducing me and other faculty members. Now what I'm trying to do is, because the time already we have lost half an hour, so the topic of my presentation is going to be machine learning approaches for high dimensional database. The workshop is on high dimensional data and how the new AI-based algorithms are penetrate into the area, so that we can able to do a lot of what do you call advanced statistical analysis, which otherwise cannot be done. Okay. Now, my presentation is going to be something like this. So just I will give a brief introduction, then give some examples about the high dimensional database, then very brief review about machine learning approaches. Mainly, I will present the results on some of the model high dimensional databases where we have applied the machine learning approach and the results. Then lastly, the survival data, high dimensional survival data. Survival data itself is a problem, but still what we are going to do is, apart from censoring, when the follow-up period is going to be very high, and it is going to be with a lot of high dimensional databases and applications. So this is the area, this is what we are going to do.
Sir, excuse me, Venkatesan sir, sorry for the disturbance.
Yeah.
Actually, now since we enabled the unmute facility, everybody can unmute. Now what I will do is, I will mute all, then you unmute yourself and speak. Others cannot unmute, sir, because I have taken the control over it. I will mute all. Okay, sir. Then you have to again unmute yourself and speak, sir, please.
Okay. Just.
Okay, sir. Now you unmute yourself and you can speak, sir, so that others cannot unmute themselves. Okay, sir. So there will not be any disturbance at all for your talk.
Okay.
Yes, sir. Yes, sir. Yes, everything is all right. You can proceed, sir.
No okay. Thank you, boss. Thank you very much. Thank you. Now everybody can able to hear me. No problem, isn't it?
Yes, sir. Yes, sir.
Yeah, fine. Any disturbances, Sundaram or Radha, just you can call me in the by phone. Okay, the outline of my presentation is going to be something like this. So what I will try to do is, I am not going to discuss any big theory about it. I am going to introduce the topic. This is for the persons who are not very familiar with the machine learning. So those who are not familiar, you take it as an introduction. Those who are familiar, you take it as a revision. Okay, with this, we'll go for this one. So, all of you know, it has been said that in traditional statistical methodology, we assume many observations and very few selected variables. That is, when the number of variables will be very low and the number of cases should be more. Even in a conventional thing for a regression problem, where you want the asymptotic properties has to be satisfied, the theory says 1:40 is the ratio. That means more number of cases than the what do you call the number of variables. But most of the times we got very large number of variables than the cases. So the observations are more than the number of when the number of variables are more than the number of cases. We call the data as high dimensional, correct? Then data of high dimensional data is very much available in almost all the disciplines, starting from medicine, because basically I wrote another field of medicine, then finance, science, etc. The existing methods are not adequate because we are having 10 variables, 100 cases, we can do very good analysis. On the other hand, 100 variables, 10 cases, most of the times, all our classical statistical method fails. So here only we want the machine learning approaches. To give some of the examples of machine learning, some big data examples. I think okay, fine. So the first one is, you take a simple image. The image conventionally, what you assume, even if you take 8 by 8, there are going to be 64. So conventionally, for any image, we are having 256 by 256 matrix. That is the maximum pixels we can have it. That is, in terms of variables, we are going to have 65,536 variables for a single image. That is for a black and white image, gray image. If the color image means the number of variables will be power 3. So many variables are going to be there. At the most, we will have about 100 cancer and non-cancer images, where you have to identify this one. So you cannot do any classical analysis using the existing methods. The second one, classical example, the microarray, where using a microchip, you can be able to get the information of any gene from any person, gene information anywhere from 6,000 to 15,000 or 20,000. I may have, as I said, I may have about 100 cancer and non-cancer patients, where I have to identify which are the genes associated with a particular disorder. Again, all my statistical methods cannot help for existing things. This is another data set where you can able to see the data is available, 60 cases, and there are 7,129 variables are there, and the CNS involvement. And other division group from Associated University, you are having 2,500 variables in 123 cases. And one of the things is, we are having about 2,053 variables in 801 cases, which is the cancer gene expression. And skin cancer, we are having about 10,000 images, but the number of image variables is going to be 65,000 minimum. And lastly, for the survival data, there is a diffusion B cell data. We are having 240 patients information, where the number of genes considered as 7,399. The patients have been followed up for a period of time to identify which are the genes associated with lymphoma, and the coverage of median follow-up is going to be 2.8. This is 132. In other words, after 240 to 132 patients have got the information. That means we can able to get the median survival. But look at this data, where 295 is there, 6.78 have been taken, and the occurrence is going to be only 79. Only 79. So these are the databases available. So the context which I am speaking is, these are the available data where our conventional statistical methods cannot help us to do the analysis. What is the other way? So one of the approaches, recent approaches, can we borrow some of the concepts which are available in the AI-based techniques, particularly the machine learning approach. Machine learning approach is a part of the artificial intelligence, is the core area. So how to make the machine to learn and do the work, right? This is going to be there. Now, from the examples, we can be able to see what is the major problem. First, the data is high dimension. So most of the times, we cannot be able to download the full database to do analysis. So what you do, the only segment of the data you will get it by sampling. So all problems, so sampling will be there. The second important thing is all the variables are highly related. All the variables are highly related. That means we are having 15,000 or 20,000 highly related, correlated variables. Most of our things we are assuming independence. And all our statistics we always used to teach only like this. Start with the hypothesis, frame the experiment, collect the data, then try to answer the question, correct? So here there is no such question like this, because there is no specific, the data is not collected with any specific hypothesis. All the information has been collected and deposited. Just we have to, so even to generate hypothesis for this one. And the most important problem is, as we said earlier, whenever the number of variables are much more than the number of cases, all my classical statistical method fails. So what is the alternative? The alternatives are going to be, there are two things. As I said, no, because the first one is going to be, is there a dimensional directionality? I think the previous lecture, Professor Sampath was telling about the principal component. That is one of the, what they call a method when variables are highly related. You can able to reduce the dimension by the instead of the original variables which are highly correlated. We can transform to certain latent variables, what they call as a linear combination of all the variables. Of course, now we got non-linear principal component also. So what we are trying to do is that all the information contained in the large number of variables can be extracted into certain latent variables, where the first component is capturing maximum, next following this one, but they are mutually independent. That's going to be the linear. Similarly, we're having non-linear approaches also. Then this is for the transformation, where all the variables, we are not leaving any variable, we are trying to capture all the information contained in this one. The second method is selection based, where a large number of variables are given. I try to extract only the most important variables. Other variables which are not going to explain the observation, just we are going to leave it. So, as I've been okay. So, sorry. See, as I said, no, the extraction method, the postman is PC principal component. Other most of the partial least square is another method, where in PC assume the xi's are fixed, where in PLS, even not only the Y, even the exercise can be random. That is the other thing most of you know. The other important thing where we are using is the discrete wavelet transformation, which helps us in most of the cases. Of course, surface pressure is one of the methods that has been classically available based on this to remove variables which are unimportant based on the correlation. The next one is the feature selection. The genetic algorithm is the most important one. It is one of the most optimization technique based on the hardcore biology. And it is called as near optimal or it is the near optimal solution. The next one is going to be fuzzy logic. And rough set is the recent area where we said, no, we can have a large volume of that to set the best subset of variables. So what we are going to do, the rough set is the order of the day, where any huge volume of data, where having 20,000 variables, 15,000 variables, to set a best subset, how to do it, that is the thing. What we are trying to do is, we try to just give some introduction about this one. Instead of explaining all the theory, I am going to say that the work which I have done, what are the results we have obtained, what are the applications of this one, and further areas for research. And of course, statistical methods for any simple classification, we know discriminant analysis, logistic regression, the nearest neighborhood, and the Bayesian. Here, for machine learning, we are having feature extraction, these are the things. And SVD, the single value decomposition, another important method. And feature extraction, we said already, we have seen. The next one is the support vector machine, the most powerful tool on decision trees. Of course, among the machine learning, the ensemble methods are more powerful. The boosting trees, the bagging, and subspace methods. With this introduction, this will say why it is machine learning. Machine learning is a branch of artificial intelligence that studies system that will learn. That is, a system that learn means it is the system that can improve their performance with experience. If more number of data is available, it can able to get better estimates, correct? Then machine learning, data mining, and statistics have similar goals. That is modeling for classification, hypothesis testing, generation. So all of you know, because statistics traditionally emphasizes some of the names are appearing. Okay, statistics are traditionally emphasizing the models that can be evolved solved analytically. For example, generalized linear model. And so most of the times we'll bring the parametric distribution. We'll depend on the parameters, estimation, and testing. Where machine learning basically deals with the quasi-parametric models. Some of the models are very closer to the human representation. Now, why we need this one? No, why it's coming? Okay. So why? So the machine learning, why we need machine learning? Because it is not new. If you take the medical field, we can able to see the articles. Just we surveyed the first 5-year articles. What we said, about 42% of the articles that has been published in the last 5 years using PubMed search, we get support vector, support vector mission. About 31% of them, they use neural network. And of course, the discriminant classical discriminant used about 80%. Others were having the logistic, the random forest, everything. In other words, if you take most of the classical statistics have been replaced by the AI-based techniques for having high-level data. So this is one of the area where it is encroaching for the past 5 years. Predominantly more than 50% or 60% of the articles nowadays are depending only on the ML-based or the machine learning-based approaches. So that's why it is very important. Next one, similarly, there are 4 algorithms. In the deep learning, most of you know, there are certain things, deep belief networks and deep neural network. And these are also for 2016, you can able to see lot of articles have come, the recurrent neural network. Most of the times people have used convolution neural network, particularly the image processing, everything, where instead of extracting features or selecting features, give the image as it is, so that we develop an algorithm where each layer try to extract certain features, and instead of we are extracting the feature and giving us an input, the raw image itself we can be able to give it. So that's the reason why it is picking up for the past 3-4 years. So with this background, what are the important machine learning based methods? First one, all of you, the neural network, artificial neural network. It tries to model the function of the brain. In fact, we try to capture the function of the brain in computational sense. Any number of artificial neural network cannot able to capture the brain function, but even if you can able to partially, you can able to capture, it can able to do wonders. The concept is very simple. What you are trying to do neural network, in a conventional regression problem, we are X are were mapped to Y in the inner product form. In between, so we are putting in between a layer to expand it. Anything, a thing which cannot be separated in the lower dimension can be easily separated in the higher dimension. So the concept of artificial neural network in mathematical sense is from a lower dimensional plane map all the features to a higher dimension, then use hyperplane concept to separate them. That is the thing. On support vector machine from 1995, it started wherever neural network can be used. The support vector plays a vital role because very powerful technique. Because artificial neural network is a learning technique, it is very slow, very a lot of things about number of layers, number of nodes, everything is a problem. Whereas support vector machine converts the learning problem into what you call constraint optimization problem using Lagrangian multipliers. Actually, it is based, the base is only from the Hilbert space. How to get, the concept is very simple. How to get the inner product of two vector phi of x into pi of y without explicitly specifying what is phi value. That's the concept. We got the idea only from the Hilbert space. Those who have studied analysis as a paper, you may be knowing. Then genetic algorithm, I said it is one of the universal optimization technique or real optimization universal technique. It is based on hardcore biology. There are three things. So it is based on Darwin's theory, what we call survival of the fittest, where the persons with higher fitness will contribute more to the next generation than the persons with weak fitness. That is the idea. So what we are trying to do is, in all other optimization technique, we will try to generate one solution from there, even linear program, one end to another will move. Here in genetic algorithm, we generate several solutions simultaneously. We try to optimize everything. Then at the end of this one, we'll get only the maximum fitness solutions will be there. Lot of solutions will come. Very powerful thing. On decision tree, fuzzy logic, and rough set algorithm. There are related techniques also, the hidden Markov model, where I think most of that things, you know, in whenever you are having certain signals, we are observing how to find the underlying state. Where in a conventional Markov chain, you are having one-to-one correspondence between Markov, the observed state and hidden state. Here, two or more hidden states can have the same signal. Given the signal, how to get the underlying state, that's going to be very powerful. And MCMC algorithm, all of you know, it is called as a model liberation movement. By model liberation movement, you construct even a model with 200 parameters, 2000 parameters. Still, I can able to get an approximate solution. So that is the idea of Markov chain. Markov chain is very simple. What you are trying to do is, whenever you are having a complex problem like this, where the parameters are not data mill, I mentioned with what you call the relator. For each parameter, construct a Markov chain, allow it for a long time, so that you get the ergodic limit. Then use conventional what you call Monte Carlo simulation to generate the distribution. That's the thing. So in this way, you can have any number of parameters. Cellular metabolism. The next important thing is, most of the times you won't be getting a single algorithm. So we try to run the genetic algorithm, get the solution, then give us an input for what you call neural network. Performance will be there. Fuzzy logic or offset as a first step, then you will have a neural network. Then most of the times you will have the structure prediction. For example, the front end you will have the neural network, back end you will have the hidden Markov model, a combined technique and able to perform better. Similarly, most of the time the hybrid techniques are needed, not a single thing. As far as database concerned, we will be having only three major classifications. It will be logical, where we are having going to have the symbolic decision tree, everything comes under this one. And probabilistic neural network, hidden Markov model, support vector machines, everything comes there. And mixed means Bayesian networks and what you call stochastic programming, etc. Now with these, just to start with the neural network, one of the oldest techniques, still powerful for making classification and prediction. Yeah, very powerful tool. Just to start with one simple example. So to how to define neural network in a formal way, artificial neural networks are massively parallel adaptive networks. That is not ADOPT, ADPT, adaptation due to Darwin. It is brain is supposed to have parallel architecture. Then it has simple non-linear computing elements. And some, so what we are going to try to abstract and model some of the functionalities of the human nervous system in an attempt to partially capture some of the, correct? Only partially capture this one. So that is neural network. Why neural network is so powerful in terms of statistics? Because the feed-forward neural network with no hidden layer is nothing but our generalized linear model. If we are having one hidden layer, that is our projection cluster regression, which is the highest level of regression. I think those who are interested in this one, the 1985 book volume in Annals of Statistics there. all regression can be obtained as a particular case of this projection feature. Of course, your probabilistic network is nothing but your discrete analysis. And similarly, we are having, for most of the multivariate statistical techniques can be obtained as a particular case of the neural network. So that's why still it is popular in the context of doing high-level statistical analysis, correct? So there are two major things. One is going to be what we call the multi-perceptron based neural network, where x's will be there and there will be hidden layer. If you remove this hidden layer, it is nothing but the conventional regression problem. Xi is mapped to y1, so etc. Is the inner product concept we are going to be there. But here we are going to map each x1, we are going to map each of the hidden layer. In fact, if you think this one, each of the xi with h1, it is nothing but our logistic regression. Because ultimately we are going to the inner product, we are going to use some function to square the value in between 0 and 1. Whenever the value is above a certain threshold, you will communicate to the next layer, otherwise it will be there. In other words, each of the input layer vectors with one of the hidden nodes is nothing but our conventional logistic regression. In other words, a multi-layer perceptron network can be thought of as a generalization of your logistic regression, correct? It's going to be there. Next one. The radial basis function, other neural network. The advantage of this one is the multi-layer perceptron neural network, the number of nodes, the number of hidden layers, and the number of nodes in each layer are arbitrary because you have to do only trial and error. Whereas here, the radial basis function, it is what is this? Something is okay. So what you are having is, irrespective of the size, the dimension of the data, the what you call the neural radial basis neural network have only one hidden layer. That is one of the advantages of this one. And it uses the kernel function, because anything on kernel function, the kernel function is the most efficient function in statistics. Most of you know about this one. And okay, just one information there we have said no how with the performance this one. So the multi-layer for the same data where you are using a logistic regression, we are getting the accuracy of correct classification. A case as a case, and sensitivity is nothing but calling a case as a case. Specificity classify a control as a control. So about 70% where it can able to do this one. Particularly the radial basis function, about almost 97% correct classification, very good classification in any biological context. Remember that in most of the application, the RBF, because it's based on kernel function, it performs better than MLP. Then, because the topic is on high-dimensional database, correct? So what you are having is a structure prediction. A structure prediction is just don't bother much about the biology. What you are going to say is, suppose given you take any cell from us, if you sequence it, it contains of the 4 letters. It still consists of 4 letter ACGT, what you call the nucleotides. The length of the string is going to be 3.2 billion. That's the length, 3.2 billion. That what we are going to do is, after this one, we want to identify which are the portions coding for some protein secondary is supposed to have 3-way classification, let us say alpha helix and beta sheets and coils, and how to make it. In other words, given the sequence, we want to classify the part into the length of the string. What is the dimension here? 3.12 billion. That is the number of strings consists of this one. So how to do it? So just to be the database, protein structure databases, any of the disease available in the protein database freely available. And this 3D structure, this is a 4D structure. 2D structure, the protein family is available. From these, we extract the features. About 8 features we have extracted. So what are the relative frequency? I don't know. Sorry, some problem is there. Yeah. So what I am doing is just extracted about 8 features. One is the relative frequency of each of the what you call the alpha theta. This one is the 3-way classification in each of the relative frequency. Then proficiency score, then E scores. Based on this one, it's a biological thing. There are, based on the huge volume data, the sequence, we extracted what I call about 8 features. Then these features have given us input for this one, where we got about about 90% correct classification. There are about more than 40 algorithms available for this one, where the same GOR algorithm is supposed to be one of the best one. and that gave only 42. We use what you call the feature extraction method using the conventional thing, and we about 8 features can be able to do it. This is one thing. The other one is there are two stains. One is the, suppose we are having COVID now. Now we are having COVID. So suppose COVID-19 is there, how to 19, how to compare this one. So whenever the sequence are available, take the sequence. There is going to be again, it is going to be a lengthy sequence. You have to take the proteins, conserved proteins, then construct a neural network. We can able to identify how far the what we call, now what we did was S37RV is a control stain, normal stain. CD15 is the most virulent TB stain. We compare this one using a neural network where we can able to see about 3% to 164 base per insertion that makes the virulent. In other words, the whole idea is using neural network, even the high dimensional base can be classified. We can able to identify what is the difference between these two things. So which cannot be done otherwise. This is only example to show you this one. So again, you are having a very good classification. You know, most of the machine learning algorithm, what we are trying to do is a huge database is there, about 60 or 70% of the data is used for building the model. Remaining to 30% of the data is used for validating the model. Even you do a logistic regression in machine learning, what we used to do is about 70% of data is build logistic regression. Remaining 30% data, how correctly to predict, that's the measure, instead of using our pseudo R square or something like that. So, now, the SOM is what you call another neural network, self-organized map. So only just to tell you, suppose these are the images of a malignant cancer patient, and these are the pictures of benign non-cancer patient. We can build this. So in other words, using a neural network to support what you call the neural network, what you call self-organizing maps, I can be able to visualize what is the contribution of each of the features, each of the variables. Suppose radius, just have given text or everything, and A can contribute. What is the contribution of each one? Also, I can be able to look in. In other words, any variable, the overall classification or overall prediction, what is the level of contribution for each one of them? So this can be able to write the price. Sorry. So these are this is another type of network where we did for one of our data sets. The other important thing is the neural network can be generalized in so many ways. One is the Bayesian neural network. But Bayesian, instead of having the nodes as the fixed, we say that it is follows a distribution instead of WAXI and as a constant. We are going to have a function. It's a more general form of this one. So that Bayesian neural network performs better than naturally other networks. That is going to be there. And of course, what are the technicalities involved in the learning? Conventional learning will have this one where we are having Bayesian learning, we are using the function. Of course, these are the technical, don't bother. The other network is a convolution neural network, correct? Where I said no, convolution neural network. I don't know why it's popping up. Anybody can help me why it is popping up?
Sir, please.
Some kind of always is something is popping on the screen. Okay, let's see. Now the next one is the convolution neural network. So this is the network which I mentioned earlier. What you are going to do is in all other kind of neural network support vector machines, given an image, you have to convert it. Either you have to use that and what we call extraction method to get the variables, and you have to give an input so that manageable. We cannot have 65,000 variables, so use in the image a principal component, a partial least square, or some transformation to reduce the number of variables in the transform, what you call the latent variable, give us an input. But here, the conventional neural network, what you are going to do is give the images as the input. So what you are doing, the first one, the images are given here. Then you can be able to see this first part of the network, try to extract the features. From each of the image, you try to extract one or two features. Ultimately, the neural network comes in the second part. It's a very powerful tool. Nowadays, most of the things, the image, the algorithm can be able to take care of it. But remember, everything based on hardcore mathematics because it's going to be non-linear transformations. Then support vector machine, I said, no, it is one of the most powerful machine learning approach for a classification. Whenever we want our two groups, we want to separate the two groups. The support vector machine has been used as a classification problem. It is used even as a what you call prediction problem. What we are trying to do is, suppose these are the two most small margins. The why it is called as vector, these are the lines. So this is the line, and you can have the two margins on the either side. the points which are on the line of maximum separation are called vectors. They are called support vectors. That's all. Correct, vectors in conventional form. And the machine, why it's a machine? Because somebody is in statistics. Some of the times we will use certain names where just like bootstrap and jackknifing. When Efron was asked why he called bootstrap and jackknife, he said he is called 2K is called bootstrap, so I called jackknife. The jackknife I called bootstrap. So what you are trying to do is, this is the called vector, support vectors. Next, so the feature separation is very easy. What you are trying to do is, suppose all the points out the circle are going to be the cases and all the points in the circle. Yeah, 2 dimensions. What you are trying to do is apply certain transformation so that from 2 dimension map it to a 3 dimension, then the hyperplane can be able to separate all the red points above and all the cases above and the controls above. So this is how almost all machine learning algorithm works. Given a lower dimension, try to make it. If the structure is going to be very complex, we need more dimension mapping. Otherwise, it's going to be so mathematically. You are trying to map it to a high dimension. Use hyperplanes for them. Okay. Then I said no. The machine learning. It's a constant optimization problem with Lagrangian multipliers. I said. So where are we getting? There is a message theorem, which is one of the SQ can be embedded into a framework of kernel into Hilbert space. They embed input space X into a high dimensional Hilbert space H with the so-called map. In other words, this is the thing where it helps us to learning problem has been converted to a constant optimization problem. Any optimization problem is more efficient, what you call in terms of this one, even more quick and give more reliable results than other things. So that's why, and almost most of the neural network problem has been replaced by support vector machine, even though it was started only in 94, 95, then it become very important support vector machine. As I shown earlier, most of the articles now they got support vector machines. Now, what is this one? You see, a 3-way classification. I want to do it. A support vector machine can be able to give me this kind of classification. It is more flexible. You can able to draw it is a MATLAB diagram. Sorry, this one. So, a very powerful classification tool, not like other things. So, more flexible. It is because it is a parametric form, not like splines where you are going to do it. It is one of the most very powerful technique for doing this the kernel functions. Correct. So, support vector machine. Then. So, to be mathematical, what you are trying to do in multi-layer function, this is the data you are having, perceptron layer. You are having the data, the closeness is going to be defined by this function. Whereas in the radial based function, we are having a finality parameter here. Where in support vector machine, you are having this is the finality parameters, correct? So, in other words, there is hardcore mathematics for each one of them. If you want to do some research, this function can be changed, you will get a better result. Similarly, for radial based function, here the finality parameter can be, but here we got a lot of options for this one. A lot of work has been going on this area, particularly for out of this omega, correct? Then the other area is the fuzzy, because except most of the biological databases, they are fuzzy in nature. How? Because we are having, you take even the textual nature, because we said overexpressed, underexpressed, co-expressed, and all the things, So most of the times, since all our statistics, what is fuzzy, because what is imprecise information or the vague information. So fuzzy theory belongs to a set or not. In classical set theory, the element is uniquely treated. A set is uniquely treated. Crypt set means either a point belongs to set, not to belong to. Here in fuzzy, in blank, partially belongs to, partially not belongs to. That's the concept. But rough set is the most important one, generalization, where the boundary regions are not by partialship, they are used by the indissolubility. So simple logical truth is 1 + 1 is 2, but you are having grass is green. I think most of you know how the what you call linguistic variables can be framed, and the things which cannot be quantified, vague information or implicit information can be quantified. For students, those who are having some problem in understanding this one is very easy. Suppose I say a boy got, suppose I say a person got 28. I say his ages could be around what you call 28. I got some what you call implicit information. But if I say his age could be possibly 20, then we say it is almost vague information, correct? And if I say if the boy is very young, that is going to be fuzzy information, correct? So most of the times, so what you are having, if a person we are having, most of the times you are well trained. Suppose a person age is 60 years and what they call weight is 40 kgs and your height is going to be 160 centimeters. We got very good methods to do it. On the other end, old person, average height and overweight, something like this, then these kind of things are there. But most of the biological information are real world problems. Everything is fuzzy in nature, and that is one of the important things we have to do it. Then rough set, I said the way concept is in fuzzy is replaced by two precise concept called the lower and upper approximation. So it is something like this. This is the set where we are dividing into three things. This is the lower approximation. That is all the points, all the elements within the lower bound is going to definitely belong to the set. Those who are outside the upper bound are not belong to the set. Those who are in between these two, they are called fuzzy information. Sorry, rough information, and that has to be based on this one. We'll put it. So it is by approximation, lower approximation and upper approximation. But the rough set is the most powerful tool for selecting a best subset of variables, correct? Even in a highly correlated condition. That is more important. That is the order of the day. Of course, we are having inner set, we are having soft set, we are having other things. So this is the area where a lot of research is going on. And the other important thing is the rough neuron, the neural network, even each of the things we said, the other important generalization is make each of the node as what you call rough neuron. Rough neuron. That means you are going to upper bound, lower bound for each of the nodes, not a fixed point. Then that's the generalization, where it is one of the powerful techniques, correct? Now, with this brief idea, just we try to talk about some of the examples. I also already the database I have shown is the database available in the website is given. There are 60 cases where we are having 7,129 variables are measured in this one. Now we want to do a classification problem. What we are trying to do is just to apply genetic algorithms. So totally out of these what you call 7,000, various combinations have been tried using genetic algorithm. Ultimately, the best subset using genetic algorithm up to 496 variables, original variables. Remember, selection. It is not transparent. So then you using that one, I can able to get about 86.5 correct classification. Then fuzzy, totally subset values of about 37,000. It ultimately boils out to be about 321 best set variable that has been there. Out of how many? 7,129 variables. We can able to get it 321, and correspondingly the classification algorithm gave us 90%. And rough set, of course, we are having the maximum because it's going to be detection of both rows and columns, and we are going to 49,000 subset have been evaluated, where it gives I think 245 best vertical variables, 245 variables, and the classification accuracy is going to be there. Now the last one is, suppose you combine fuzzy with what you call rough set, and with the hybrid combination, of course, evaluates more numbers of subsets. Ultimately, it turns out to be 114 variables. With 114 variables, I can able to get 98. So, whenever not only that, even neural network, what used to do is a fuzzy neural network and a neuro-fuzzy network. So, what you will try to falsify the data, give us an input so that the classification is better, or get the output from a neural network, falsify the data, and try to get so that there will be overlap, other indices can be handled probably. So, just to say that a rough fuzzy combination can able to result in 98 correct classification of the previous data set, which is high dimensional data set with 7,129 variables, only with the 60 cases. So this kind of analysis cannot be done using any of our conventional method, correct? Okay, second one. We take the next example, image database, which is awesome. There are 2,500 features, variables have been considered. This one for each individual. There are 121 patients. These references are given. Similarly, we try to have the different groups. Genetic algorithm, fuzzy, rough set, and the neural network, and rough neural network we tried. What you can do is, the rough neural network can be able to give a better classification than all other methods. But remember, anything of this one, anything related to fuzzy, and here in this particular case, the neural network, everything above 90. And the fuzzy neural network can able to do 99 things. Upon number of attributes also selected variables you can able to see. Here out of how many variables? Out of 2,500 variables. Of course, the genetic algorithm can able to only half of the variable, about 1,014 variables. Whereas fuzzy can able to get the out of this one 916 subset, this subset. Here 754, here 713. Both the combination put together, the number of variables are there, and of course the classification also up to 95%. Correct? This is going to be one of the important thing. So with this, next about 15 minutes we'll talk about the other type of eight-dimensional database. What you said, thermal analysis. All of you know it is one of my field EAD research, because I was one who started my research EAD is in this one surveil analysis. So surveil analysis, what you are having? When you have a group of observations, and the data is going to be a follow-up period, because it's going to be time from the starting point to experience of particular event. It is measured on this one. So study of duration between any two events. And what is the definition of this one? So first one is the time origin should be well defined, and the scale of measurement should be uniform. And next one is the meaning of failure should be clearly defined. And censoring is a major problem, because when you're having 100 patients were admitting, after 2 years you want to get the database, at least 20 or 30% of the patients will be lost, or in between died, or they could have been there. What we are getting only partial information. Missing data is different. Sensor data is different. Sensor data, that is, I am treating the patient for past 3 months. I want to give the treatment for 6 months. The patient has taken 3 months. He is not cured, but he is lost. That 3-month information, we are classical statistics, we are eliminating it. How the best way to incorporate that is going to be there. So that is censored information. And there are a lot of censoring. One is called type 1, type 2. Then we have random censoring, type censoring, interval censoring, etc. for each one of them, correct? Now here, I got a high dimensional database where I said initially the data where I 2.6 years, where the patients are followed for about 7 years on the immediate period with the 3 years. Now I want to do an analysis for, because it has got the number of observations are so high on each of the individual, and some cases censored more than 40%. So what is the statistical problem? Whenever set of observations comes in, always you assume IID, no? The IID assumption, even some set of values are greater than 2, greater than 5, greater than 3. Then your mean will be greater than something, your variance will be greater than something. That means all your classical methods, t-test, ANOVA, everything, whatever is it is not applicable, whatever it is in this one. So what you are going to do? So the first thing is the, what you call, the surveil function is nothing but the 1 minus distribution function. It is a probability of t greater than small t. Then density function. Remember, whenever you want to calculate the x of x, because x we have done, because censored, x, but the unifying concept is either density or distribution cannot be specified directly for a censored a set of values which contains some sort of observation, but hazard function is the unifying concept. It doesn't involve the censoring time. So from the hazard function, you can be able to get the density distribution very easily. They are highly connected, right? And most of you know about this one. And classically, what you used to do, whenever you are having an observation, only R or full observation, we take this one, only unsought observation. We know it is a highly biased estimate. And the type 1 censoring, the number of what you call period is censored. I will start the study after 2 years. I want to stop it. That means number of failures are random, failure types are random. In other words, in classical sense, what we are trying to do is, what is the statistical problem here? For a one, because inside the classical statistics, you always play with sufficiency. Sufficient statistics there means it contains all the information. The sample information contains all the information, the parameter. Here, for a one-dimensional parameter space, I am getting a two-dimensional what you call sufficient statistics. This we call it as what we call in classical statistics, we call it as curved exponential families, correct? Similar, but in type 2 censoring, we are playing what we are fixing R. That means one parameter is all fixed. That is still is one parameter. So that's why type 2 censoring very easy. Most of the people working on this one. Type 1 censoring, where It will be for one dimension, even for the mean, we are having two dimensional sufficient statistics. That is the problem. The random sensoring, here the sensoring time is random, the response time is random, and everything random. So in a random sensoring, for a one parameter space, we are having three dimensional sufficient statistics. So these are the problems. So these problems from 1958 to 1972, where Cox have opened the whole field of the what you call Cox regression model. Then 1975 introduced the partial likelihood everything to incorporate even the incomplete observations or the partial information, so that we get the estimate instead of eliminating, because that is going to be there. No. Now, how these concepts already we know can be extended for a high dimensional database. That is the my aim here. So what we are having is the basic Cox model, all of you know, because it is called the proportional hazard model, 1972. If you take the past 20 discoveries of 20th century, only three things have come from statistics. One is the first one. The second, number two, is the chi-square statistics by Carl Pearson. The next one is going to be Fisher, who is there in the 7th or 8th place for his design and test steps, everything. And the third one, the third statistics you will find that the top 20 is D.R. Cox for his partial likelihood approach. Correct? These are the three major contribution statistics in the top 20 discoveries of 20th century. Correct? So that is going to be there. Then what you are trying to for a high dimensional database, we try to all the regularized Cox. There are lasso. Lasso is one of the important Cox because for high dimensional database, particularly introduced in 1996 by Cipserani. Then we are having ridge Cox. The ridge already we know. Whenever we are having multicollinearity, we try to introduce certain bias to stabilize the variance and here this can be extended. The L-net Cox, L-N Cox, and Oscar Cox. These are the on Cox most time dependent. So these are the generalizations that has been done in the survival analysis to account for high dimensional database. That you have to remember. First one is the regular. What we are trying to do is for lasso Cox. This is the model, the regular Cox, the Cox model. It is going to be, so don't bother much about the next step to say that lasso Cox uses what you call an L1 norm. L1 norm, correct? Ridge Cox use the L2 norm. There is going to be the correlation. Then L-net Cox combines the what you call a convex combination of the L1 norm and the L2 norm. Then adaptive lasso, etc. In other words, these are some of the what lasso Cox is. So, in simple terms, what I suppose you are having 15,000 variables, I am fitting a regression line. The lasso, what is, which are the variables which are having not independently, you will force them, the betas will post to 0. That means most of the variables which are not related to the outcome variable, for example, it will force all the variables to 0. The betas will make to 0, and only the best subset will be retained. That is lasso. It is syncage estimate. It is nothing but lasso is nothing but the syncage estimate. And the other one is lasso Cox. So there are three versions for this one: adaptive lasso Cox and our infused lasso Cox, graphical Cox. The ridge Cox, what it is, it also does the same thing. Whichever the variables are not important, it will force the betas very near to 0. Only certain important variables, the betas will be retained. All other betas, whether the dimension is going to be 20,000 or 2,000 number of variables, it will force to 0. The only thing is, but it won't make it 0. Whereas lasso makes the unimportant variable betas as 0. Here it will make almost 0, but it won't be 0. That is one of the things, correct? And L-net Cox combine both the things, where it will force some variables to 0, others very near to 0. One is the best subset is being done, correct? There are other methods, the extensions that has been done, and the powerful method. These are the recent developments, particularly for the past 5 years. Lot of work is going on this one, where any parameter you can able to, there are a lot of open problems here. The Oscar is nothing but octal linkage and clustering algorithm. You can able to see this one. It is lambda 1, lambda 2, where lambda 1, lambda 2 is going to be constant. Convex is only. And the perform variable selection for highly correlated features, because most of the times we are doing biology, the variables are highly rated, highly correlated. That means, and we are having a gene where I get 15,000 gene information from each of the individual. I am fitting a regression with the 15,000 variables. Naturally, all the variables are highly rated, correct? So in such situations, the extension of the what we call the regular use methods, the lasso, the ridge, the L-net cox, and of course other versions perform better. In other, you can be able to get a best solution for this one. Otherwise, conventional what you call the methods. Still, because in logistic, in surveil analysis, still the problem is there. The number of variables should be less than the number of cases. Correct? The number of variables should be less than the number of cases. That question is there. But nowadays, when you follow study, where I want to identify, follow the patient for 2 years, I want which are the genes constituted by a particular longitudinal study, where each individual is supposed to have over 32 or 33,000 genes, out of which I will narrow down, I will get at least about 15,000 or 10,000 genes are very important. The gene information I am going to measure over a period of time, whether it naturally or under treatment, where it changes, then that data is a high-dimensional database, which cannot be analyzed using our conventional surveil analysis techniques available. This can be extended. So these are the other extensions that has been done. Okay. Similarly, cock boost, I think a boosting algorithm, one of the things, because bootstrapping very powerful, where it tries to have it, the Cox boost, the goals are similar. They estimate the model. Difference is the one makes the component-wise boosting, where otherwise like all flexible candidates are the variables. They're slightly there. Similarly, the time-dependent covariate, correct? What you are trying to have is, suppose we are having a set of variables, where, for example, age is a time-dependent covariate, correct? You are measuring one and you are following study. After 3 years shooting study, still you cannot take the initial age, correct? That age could be varying, and some of the parameter initial value. So, for example, gender is time-independent, correct? No problem. But other variables, most of the other variables could be time-dependent. So, you are having a combination of dependent and time-dependent, time-independent covariates. How this will be handled? So, time-dependent Cox model extended for high-dimensional database. That is work is there the past 5 years. A lot of work is going on this area, and these are some of the technicalities. How to calculate hazard function for a time-dependent. You can able to see, those who are having these are dependent covariates where having two components, and the hazard function we are going to calculate. This part, first part contains the time-dependent part. The second part contains the time-independent part. Correct? This is conventional part. If the other models, we just will have this term won't be there, only this will be there. And so the first component to expect the time dependent on this one, and lot of work is going on. Still, a lot of open problems are. So these are the areas where, so high dimensional is the area is one area where lot of work is needed, where our statisticians venture on this one. My whole idea is to see that this is the field where open and where our people can survive for next 100 years without any problem. That's the whole idea of introducing these topics. And then we'll come for the machine learning approaches for how this can be extended. So the machine learning. What are the machine learning approaches? Surveil analysis, we can be able to do it. So surveil trees, we know decision trees there, we can extend the surveil trees. Bayesian method, particularly Bayesian methods, you can be able to see Bayesian, naive Bayesian and Bayesian network. The only difference between these two is here this assumes independence, where Bayesian network it can be, need not be, the exercise need not be independent. That's the thing. Of course, neural network can be extended. Again, we are having support vector machines have been extended. Advanced machine learning, where having the ensemble methods, the active learning, transfer learning, particularly multitasking. The active learning and ensemble, most of you know, these are the areas, core areas we are doing. Even ensembling, all of you know, those who are doing data mining, these are the three areas. One is going to be the bagging, is going to be boosting, and the random forest. And these concepts can be extended to a high-dimensional, what I call surveil data using our machine learning approaches. Correct. So the random forest can be extended to surveil random forest, and bagging trees can be extended to bagging surveil trees, and boosting algorithm can be extended to high-dimensional database. For surveil data, correct, duration data, with sensoring is part of that one. Remember, there's going to be, we are not dealing with any regular exponential families, not only exponential families, even we are having so many other things where we have to get some what I call quick answers. Surveil tree, all of you know, because surveil analysis, how tree can be done. The log rank test is more commonly used for dissimilarity measures in surveil analysis. This has been extended to surveil tree also. Then the bagging, because bagging, boosting, bagging is nothing but boost up aggregation, correct? So what we are trying to do is, we are having one data set. Normally we used to do most of the resampling plan. We are having what you call bootstrapping, where you used to do it whenever your database is not there, only sync data bit is done. With the replacement, we generate large number of data set with replacement, then try to fit the model for each of the samples. Suppose you are having data set 100. So with replacement, generate data sets of 100 size with replacement. How many things? 1,000, 10,000, 20,000. Each time fit the model. Try to aggregate this one. That performs better than the existing one. That is one of the what you call. Classically, we used to call as variance reduction techniques. Correct? That's going to be there, where the mean is going to be same. The same concept when extended even to sensor data. Correct? That's going to be there. Of course, random forest. Random forest, one advantage of random forest is your data set is randomly you are going to select each of this one and try to fit it. Where whenever you are having sensoring position, there is going to be some kind of missing values. So this takes care of better than other methods, correct? It is going to be there. So random forest observability is a very powerful tool and lot of work. Here one concept most of you know is the OOP, out of bag data. So one of the important thing is also 63% of the data is always used for considering the trees. 33% of the data is left every time when you are fitting. Repeatedly, we are going to take and we are going to construct the trees and we are going to average it out, which gives better what you call estimates for the parameters than other things. Of course, these are the other technicalities. Similarly, support vector regression. Because I said support vector is a very powerful tool. It can be used as a regression tool given for sensor data, how this can be extended. We got a lot of powerful things. Ordinary sensor support vector regression is there for what you call full observation, no problem. But this can be extended to sensor data also. And it has been recently, a lot of work has been carried out on this area. Of course, these are some of the technicalities we given for sensor data. A neural network, how neural network can be, because in neural network, whatever you consider, the database is full. But we are having sensor observation, how this can be extended. Machine learning, yes. There are Cox proportional model with how to build a Cox regression model, neural network. Lot of things are. The only thing is how the linear function. There, in classical neural network, we'll get excise, sum the excise, the inner product, correct? Then use certain transformation to take the values from 0 to 1, fix a threshold. If the threshold above this, you try to communicate, or it is going to be less than 1, you are not communicating. Here you go into the softmax. Whenever the classification is going to be more than 2, actually you go for softmax function. But here, the inner layer takes this kind of thing, where the function is going to be, formerly it was only this term, now we are going to log of explain of this one, so to account for what we call the duration and the sensory. And of course, D surveil, very, very powerful tool. So start with one layer, number of hidden layers, how many hidden layers you have to do it. So the function is no longer linear, that you have to remember, because they are not going to be simple inner products. And a lot of work has been going on this area. This is only to introduce people that these are the core areas where you have to venture, you have to do it. But all basic statistics is very important, but you cannot survive with your basic statistics unless you are going to have it, because you cannot do with all ID conditions, everything, the classical. That is 1950s. 1950s era is gone. From 2000, we got entirely new thing, particularly for the past 10 years. The development is so, because of the advancement in computer, other things, we can able to do all the work, correct? It's going to be there. Then the convolution network. So this is what we said, initially the images will be there, each one of them features. Lastly, the neural part will come in the last part. The other important thing is the rank-based models. A very powerful method. Actually, it is based on what we call the boosting concordance index and of course the C index. Similarly, we are having Kaplan-Meier estimator and boosting confidence intervals, everything we are doing. In other words, in a non-parametric way, how these things can be handled, because everything is database, correct? It is going to be there. Then the other important area is the active learning. Active learning. The objective is to identify a representative sample of the data. So we are having now we got big data, correct? In the context of big data, where the volume is going to be humongous, even you cannot have a high what you call in the computer to download the database fully. So how to get a representative data from a big correct? So there are methods by which you can, that is active learning for surveyed data, particularly. So this is the algorithm for what you call active learning with sensor data, how is going to do it. So I think Those who are interested, I will give this one. About multitasking, the other one, and what you call the knowledge-based learning. So one of the important things, how to, the transfer learning model aims to use auxiliary data to augment learning when there is insufficient number of training samples. In other words, data is very small. I have only 200 cases, 100 cases. But remember any machine learning algorithm because large volume of data, correct? Large volume of data. Here it's not there. What we are trying to do is we are using a knowledge transfer. That is one of the important things we can do it. And this is the recent area. Past 5 years, a lot of work is going on this area. And what are the related topics? Yearly prediction. What you are having nowadays, even suppose we are having COVID condition, no? Now I cannot conventionally control clinical trial. If you want to give the treatment for 6 months and you want to observe for another 3 years, then another for 5 years, for minimum 10 years, data is needed to say whether before coming for this one. Now we want everything. So now what we are going to do is, based on certain markets, if you give the data, if the patient is treated for suppose 10 days, 15 days, based on certain markets, can be able to predict whether the patient will respond or not. Correct? Respond or not. So this kind of thing is the order of the day. How it can be done? There's a lot of work is going on in this area, particularly for surveillance analysis. So I can able to predict. Suppose the patient, these are the patients we are going to do it. Suppose the study I am planning on, I am starting. Here there are 2 patients who have responded, other things are not responding. Based on this one, can be able to predict this patient will respond or not, or this patient will die, yearly marker. So this is going to be there. Here the Bayesian concept is highly used. That is one of them. Now most of the clinical trial now we are having the modeling and simulation is the concept of the day, where surveillance analysis is completely dominated by the modeling and simulation. So given certain things, based on the initial values, can you able to predict that? Because normally, if suppose let us say for tuberculosis, we are giving 6 months treatment. After 6 months, you will say what proportion are cured, what proportion are not cured. Suppose I treat the patient over 2 months. Within 2 months, based on certain marker, can you able to predict whether the patient will respond at the end of 6 months or not? Or based on first month, can you able to predict this one other marker? So these are based on certain surrogate marker or biomarker. We have to do it. There is a lot of that means. Apart from the conventional surveillance analysis, sensoring, we are having another problem. Because you will be getting, if you take in this way, 90% of observation will be sensoring, only 10% will have full observations. In a classical sense, any surveillance analysis, if the sensoring is going to be more than 25% or 30%, we are not supposed to do surveillance, because what we are trying to do is, given the 75% full observation, I want to estimate the distribution of the incomplete 25% observation. We are not individually predicting the values here, but lot of theoretical work has come, and we got a lot of, this is the area, core area, where a lot of work is needed, which is based on the high-dimensional data, and a lot of new machine learning approaches come for this area, correct? Similarly, Bayesian can be extended. Most of you know the Bayesian, this one. Augmented and Bayesian network, I already told you. This is when the x's are related. This is assumes independence. And the yearly stage prediction. In other words, for one data set, just we compared, where a Cox model, linear regression, random forest, naive Bayesian, then we are having Bayesian network, all the models. So we can able to see the accuracy of this one, the percent available occurrence. So most of the times you can able to see the ESPBN seems to be performing better than accuracy, all other models. So only these 3 models, correct? The Cox model is a very low here. Conventional Cox model we are having. You can able to the top level, we are having this one, the Bayesian network. The next one is going to be, the decline is going to be, this is going to be naive Bayesian. This is the next one, but red is going to be here, yeah. So this is the, we are given the theories here, correct? These are going to be the theory. So the ESP is nothing but early stage prediction based on what you call the naive Bayesian. So we can able to see the accuracy 86 to 84% on this one, where our conventional model was using Cox or the linear regression, everything. The random forest also is supposed to be better. And the long run it catches up, but when you are having percentage available events, so whenever even the level 20% of information available, these 3 techniques perform very well, very well. Then uncensoring approach, we're having a lot of things. Then we're having calibration, one of the important area. Stratified Cox model. What you used to do is, because that's going to be subpopulation, because the population, one of the conditions we're having homogeneous, correct? Because we are in common error structure. That is one of the things. Suppose we are having 2 or 3 different subpopulations, then we try to stratify and try to get a model for this one. And competing risk. 2 or more causes operating on the same individual, where survival analysis we say that the event that is the one risk factor, and which is the factor, death is going to be one thing, whether it is due to the disease, cancer or TB, or it's going to be malaria. Where if a person is having both BP and what they call TB, the patient could die either due to BP or the patient. 2 or more causes operating simultaneously on this one, how to get the margin. In other words, the problem is theoretically is very simple. Given the joint distribution, we can get the marginal distribution even without assuming X and Y independent, correct? But given the marginal distribution where X and Y are not independent, how to consider this one? That a lot of new methods have come. So competing risk, K causes are operating on the same individual, and biological context, the K causes are not independent, they are highly related. That means your X's are highly related. So that, and this was being done, because even the dependent thing, even 1972 NADA session, after a lot of work is spent, nobody is touching on this one. Suppose this is competing risk. Yeah, person is alive, kidney failure, heart disease, stroke, other. That could be any one of this one. So what you are observing is the cause and the minimum order statistics, correct? That's going to be there. The only thing is, minimum order classical, we assume independence here is not independent, generalization occurred. And of course, these are some of the technicalities. The Cox model considers all events very powerful. In other words, recurrent event. Because if it is going to be one time is okay, common cold, we get a recurrent. We are having other diseases where the same person can get more than once. In such kind of situation, how to do it, recurrent events. And so, in other words, these are the core areas of high dimension. This is one whole idea is to introduce to you. These are the core areas, particularly even the classical sense. What are the extensions we can able to do in high dimensional areas? How this can be further extended to sensoring situation where the data is going to be duration, and this is the way review. And I think your time is up. So what are there are a lot of software, because now everybody is talking Python. R is one of the classical software where we're getting a lot of things. And classically we can able to do the whatever I said, the LN Cox, Ridge Cox, Lasso Cox, we are having the R packages there. Similarly, Oscar Cox, books, etc. And lastly, even the most of the other things, where we're having Bayesian methods, random forest, the active learning, other things. Here also now we got only thing is, the multitask learning still R is not the development, but MATLAB does well. And of course, transfer Cox is going to be the only program. I think somebody attempted R, which is not working well. Otherwise, ESP, these are the most yearly predictions. And we are having all R packages available. These are some of the general packages available. I think with this, I want to close my talk. I think everybody is hungry and people will be waiting for when to finish. So with this, I want to conclude my talk. I thank the organizers, Professor Prakash and others, for inviting me to be part of this program. And thanks to all the participants for spending their time. With this, I close my talk. Thank you all. Wish you all the best. Okay.
The floor is now open to questions.
Radha madam, you can unmute yourself and you can sum up the questions from the chat box, madam. Radha madam, please.
Any questions? Then just anybody, 1 or 2 questions, because everybody is hungry, But I finished in time, because within my time I finished.
Thank you, Professor.
The whole idea is just to introduce the topic, which are the topic, current topics, the recent topics, where in the high dimensional database, what are the works needed, what is the current situation. And a lot of gray areas are there, Those are interested, we can discuss, there is a lot of, particularly now people have become very lazy in doing PhD. This will take one partner just to get a PhD. These are the core areas where people can do a lot of work, credible work. Once you are doing, we get a lot of credit also.
Sir,
Okay.
Sir.
Yeah.
Thank you, sir, for your lecture. I have got one question regarding neural networks, sir. What is the maximum hidden layers we can have, and what is the minimum or maximum hidden layers we can have in neural networks, sir?
It depends on the complexity of your database, correct? What you are going to do is, normally we start with the suppose number of input and number of output divided by 2 is the starting point, correct? But conventionally what you do is, if hidden layer, it is not the hidden layer. Normally the theory says a neural network with one hidden layer can able to approximate more than 95% of any complex function. Okay? That means for most of our real world problems, a neural network with one hidden layer is sufficient. That is for 95%. That is a theory. So, yeah, the power of neural network is with one hidden layer, you can able to approximate more than 95%, because you said no, without hidden layer, we say generalized linear model. If you are having one hidden layer, the projection pursuit regression, I said.
Yes, sir.
That means it is going to be the theoretically more than 95% of the complex functions, whatever function relationship between x and y is you are having, it can be approximated using a neural network one hidden layer. The only thing is how many nodes we can have in the hidden layer. That is, you have to start with what you call the input out layer. You start with the minimum, you can go on. It is only trial and error, correct?
Okay, sir. Thank you, sir.
Okay.
Sir, Dr. Rahim, sir.
Yes, madam. Yes, please, madam.
Sir, I'm not able to get chat box live, sir. Can you connect it out?
1 minute, madam. I enabled the chat now, madam. Meantime, any participants to have the live interaction with the resource person, let them raise their hands and we can allow. By the time chat questions you will receive, madam.
Okay, sir.
And you can sum up the chat questions to the resource person, madam.
Okay, sir.
Any participants want to interact with the resource person?
Any participants?
What, Viswanathan, no questions, sir.
Yeah, if you have some time, yeah, sure. இல்ல சார், எனக்கே ஒரு கேள்வி இருக்கு. Shall I
இல்ல எம்ஆர்எஸ் மைக் ஆஃப் பண்ணிட்டு போயிட்டாரா?
இந்த நமக்கு இன்ஃபர்மேஷன் தெரியல சார் இந்த பிளாட்ஃபார்ம்ல. பட் I have one question. Shall I do it?
Let's கேக்கணுமே. Now we expect the first bulletin only from you, bullet only from you.
Thank you, Professor. See, the problem is if you have a data like regression or fully numeric dependent variable, then we can use a distance function, something like y minus y hat, and then you can minimize the error, or what is L1 error, L2 error, whatever may be the thing, and we can tune the model.
Yeah.
And if you have a fully categorical variable, okay, something like 0, 1, or even more than 2, you can
independent variable or dependent variable?
Dependent variable I am talking about.
Independent variable.
Dependent variable.
Dependent variable. Okay.
Dependent variable. Then we can go for fit a model. You can go for a confusion table at the end, and you can check the accuracy. And based on that, we can fine tune or say this is best, this is worse, something like a comparison can be done, or a metric associated with the accuracy can be created if it is fully numeric or if it is fully categorical. So in case of survival analysis, okay, what is the measure that guarantees the accuracy and how it is derived?
You mean accuracy, how correctly you can able to predict, right? See, any machine learning algorithm, survival analysis is going to be, because we are based on the partial likelihood, correct? Still, if all your observations are IID, then my partial likelihood converges to classical likelihood.
I want a metric, sir, to compare my model. It's not necessarily machine learning.
The model is going to be, suppose you are having 2 parameters, 3 parameters, correct? Suppose you are having n variables, n minus 1 variable. Deviance is a criteria. Deviance, classical deviance. Deviance is the criteria we are having. For any sensor data, we are having Cox model with, you try to calculate the deviance is minus 2 log likelihood only.
Okay, so that means
a model with minimum deviance, the deviance is going to be, suppose we are having 10 parameters, we are adding one more parameter. If the improvement is R, you are from 10, you are going to reduce it to 9. The reduction in the deviance, minus 2 log likelihood. Instead of minus log likelihood, now we have got a lot of pseudo methods like BAC, we are having SAC, there are other methods by which you can be able to do it. In other words, just like any classical sense, we can be able to what they call quantify the difference, we have got measures are there.
that just one doubt with respect to that likelihood, because whether it is AIC or BIC or some
So
other
we are having partial likelihood, you know?
okay, basically we have dealing with likelihood, which is
partial likelihood, not
okay.
likelihood, because the likelihood we are having the numerator contains all the observations, the full observations, where the denominator contains partial and full observation up to the time point it occurs, correct?
Okay, sir. Now my doubt is
partial likelihood is generalization of the 1975 Cox has given. That is the revolution in the whole area. So that is the area where the whole regression problem is open to censored data.
Accepted, Professor. But my doubt is, if it is likelihood based criteria like deviance, it is something we are summarizing for the entire sample. Whereas in case of regression, yi minus yi at. In case of confusion matrix, every individual is compared with the predicted thing. Is there any such thing based on individual metric for survival analysis? Survival model.
Everything is based on hazard, boss. Everything is based on hazard, correct?
Okay.
You see, what you are having is the density of distribution cannot be specified directly. The unifying concept is only hazard function. Hazard function, nothing but the density divided by 1 minus distribution, correct?
Okay.
So what you are having, once you are having the hazard function, from this I am able to recover indirectly what is the density, what is the distribution. Then I try to use all the methods.
Okay, that means you have to go by the parameters, not by individual cases.
Yes, correct.
Thank you, Professor. Thanks
but
a lot for...
still, that is once again the problem is complicated when you are having dependency of the exercise.
Yeah, sure.
It is very common.
Yeah.
So that's why the time dependent they try to extend the same concept you are accounting for the interdependency also.
Okay, Professor. Thanks a lot.
And now one Mr. Stephen Raj wants to ask some questions, sir.
Stephen Raj.
Manoramaniam.
Good morning, sir.
Manoramaniam.
Yes, sir. I am Stephen from University. Sir, I have one doubt, sir. While dealing with analysis, whether the invariable unit of measurement cause any changes, sir? Unit of measurement. Each variable has different measurement scale, no, sir? Unit of measurement.
Definitely. There is a basic thing in statistics.
How can we deal with the unit of measurement, sir? How can deal with the measurement, unit of measurement?
Unit of measurement in the context
suppose height having some measurement and weight having some measurement. I dealing with some analysis means whether this
height, weight, BP or regression how you are dealing with measurement
yes, sir.
Hey, see, the thing is, whenever height is going to be a different scale, weight is going to be another scale, you need regression, we are normalizing everything before putting the regression. That's why we are doing regression, no? We have to bring it to a common scale, numerical value. Even W variable, you are trying to do the same thing. Because any regression problem, that's what we are doing here.
Okay, so the normalized course only can be used.
Okay, are there any other
questions? Thank you, sir.
Sir, there is one more question from Mogan Ragul. He has asked which programming language can be used for high dimensional data, either R or Python? Which
the best language for this one is going to be for modeling. Normally, if you are having the generalized additive models and other thing, you have to go for this one. What do you call our S plus? S plus is one thing, which is nothing but R in the public domain. The other one is, the language most of the time for building this one, I think MATLAB is a very good software, particularly for building the MATLAB. You are having the optimization toolbox, neural network toolbox, and other toolboxes are there where you can able to do. MATLAB is a very good software for doing this one. As far language is concerned, the BioPerl, or BioPerl for what you call for biological database are better than other languages, because there are certain modules are there which are useful, very easy for us.
Thank you, sir. One more question from Mangai Kartikeyan.
Yeah.
What is the limitation for high dimensional data?
What is
the limitations for high dimensional data?
Anything. We cannot be able to say the number of variables. See, the definition of high dimensional data is when the number of variables are going to be more than the number of cases. So normally, in context, the database you use, the number of variables are going to be. Suppose we are having 100 variables, 10 cases, then it's high dimensional. But normally, what we are having in most of the contexts, we are having 10,000, 15,000, 20,000 variables, and we are having only 1,000 or 500 or 600 or 2,000 cases. So where all our classical method fails, how to go about it?
Sir, only one more participant wanted to ask some doubts, sir. Madam
Yeah.
Sumitra, madam, now you can unmute yourself and you can speak, madam. Yes, madam, you can speak now, Sumitra, madam.
Yes.
Madam, you are not audible, madam. Sumitra, madam, you are not audible. But you unmuted yourself and you can speak.
She is unable to unmute, I think.
No, actually, I have given permission and she also unmuted herself, but I don't know why she is not speaking.
Then Radha can get the question from her and tell me.
Yes, sir. Then I think it is.
Yeah. Better.
No more questions. Then, madam, Jayashree, madam, you take care, madam. Care of.
Yeah. Everybody is angry because almost 1 o'clock.
Jayashree, I am handing over the session back to you. Jayashree, Dr. P.R. Jayashree.
Yes, ma'am. Thank you, Professor Venkatesan, sir, for a very informative and interesting talk on the machine learning techniques with lots of applications. And I hope some of you can take up the open problem which he has posed in this session. Thank you very much, sir.
Oh, thank you, ma. Thank you. Thanks for the organizers for inviting me. Thank Pravash, Viswanathan, Jayashree, Radha, Sundaram, and Nancy, all other faculty members for making me part of the program. Okay, thank you, and wish the participants all the best. Any questions, just mail me, we'll try to answer. There won't be any problem, we'll correspond it.
Thank you, Professor. Thanks a lot.
Thank you, sir.
Thanks a lot,
Thank you. On behalf of the participants and on behalf of the department, thank you so much, sir.
Okay, ma, thank you.
Now I invite Professor Sundaram, sir, to propose vote of thanks.
சுந்தரம் இருக்காரா லைன்ல? என்ன பண்ற தூங்கிட்டியா இல்ல உட்கார்ந்துட்டு இருக்கறியா? சரி.
Am I audible?
You are audible.
Yes.
Good afternoon to all. It's my privilege to propose a vote of thanks to my well-wisher and my guide, Dr. K. Venkatesan, scientist and retired NIRT, ICMR, Chennai. He has been giving a lot of research lectures throughout the world in the field of mathematics and statistics. Before and after retirement, still he has been encouraging and guiding research activities to the research scholars and faculties with free of cost. Sir, I am very proud of being a student.
Most of the guides are taking money.
Being a student of you, sir. Today, your research speeches have enlightened our minds and have shown us a new path. We had an opportunity to hear your research speech, and this will surely be going to encourage us in our future events. Today, my words are not enough to express the gratitude. On behalf of our college principal, staffs, and students of the Department of Statistics and participants, I express my really hearty thanks to you, sir. Also, thanks to IQAC co-director, Dr. Abdul Rahim, sir, for providing this webinar techniques. Once again, thank you very much to all who participated in this session. Thank you all.
Thank you, Sundaram. I think normally once finishing PhD candidates won't look into the guide. I think I got the privilege of seeing all my students once again. Thank you, sir.
Thank you, sir.
Thank you,
sir.
Jayashree, madam, you want to say something?
Thank you, sir. Thank you, Sundaram, sir. With this, we come to the end of the morning session. We had a very informative and very interesting 2 sessions, and I want to thank all the participants, the overwhelming responses, the question and answer sections, and we will join in the afternoon for the 3rd session. And I hope that all the participants will join us in the Zoom meeting at 3 o'clock. Thank you, Ananda.
Thank you.
Thank you, madam. Shall I wind up and we'll reopen by 2:30, madam?
Yes, sir. Thank you, sir.
Thank you.
இருக்கு. யோசிக்க முதல்ல